Mr. Cortez, welcome. How are you?
Good.
This is excellent.
I'm the only one here?
So far. It's not 1:30 yet, so we'll see. Get the camera ready. Here, back here. Pauline's here. Yes, that's great. How you doing, Pauline? Welcome.
I'm doing well. How about you?
Marvelous.
That's
Simply
great.
marvelous.
Hey, Christian. How's it going?
Good. How are you? Pretty good.
I'm doing well.
Ready for this final?
No. Who's ever ready on a final? Who's ever ready?
You guys will be fine. A-okay.
Were you able to finish, Christian? Were you able to finish the assignment? I didn't finish it.
Which one is this one?
The last one.
The filters one?
No, the finals.
The practice final.
The practice final.
Oh, honestly, I looked the other day. I didn't see it. I must have somehow missed it, but I looked and no, I didn't see it in there. So I'll do it tonight though for sure. To practice, get some practice in.
I know.
Well, we're going to review it. So if you haven't done it, then it's, then you haven't done it.
Thank God. We're going to review it.
Yeah, there's no, yeah, I mean, yeah, we're reviewing it. So, all right. Andrew's there. Is Kyle with you, Andrew?
Yes, he is.
Cool. All right. So let me go back to here. All right. So as a practice, so Andrew and Kyle, did you set up that second laptop?
Not yet. No, we have not.
Well, you can't take the final if there's only one laptop in the room.
Yeah, he has his laptop in his room at the house here.
Okay. All right. Well, then let's take a look here. So we're going to be looking at each of you. So in all this time, Kyle has not logged into Zoom on his laptop, but on your laptop,
Yes.
right, Andrew?
Yes.
Okay. So maybe this would be a good opportunity for Kyle to get on his laptop so that he can see what this looks like on his laptop on Zoom.
Okay. He's gonna go grab it now.
I'm just saying, now would be the time to practice. Tomorrow during the final is not the time to practice and discover, oh God, I got technical issues.
Yeah.
Okay, yes, we've been working all along with your laptop, which is great, which is fine. We're good.
Bring it out here.
Okay, all right. So, yeah, let me go take a look at this. And do this.
I just noticed that we've been dwindled down to but almost a handful. It's a little sad that we started off being 20 or more than 20.
Yes.
Is it always like this, or is just
no? The COVID has certainly not contributed to.
You got the charger?
Matters. Let's take a look.
Do they think in spring after summer that they're going to do the hands-on classes again?
I hope so, but that's up to the school district. You know, what we're doing in June is we have 2 weeks in June that are scheduled for us to return into the laboratory using proper PE and social distancing in the lab. So your grades at the end of tomorrow will be listed as IP, meaning in progress. So your final percentage, whatever you achieve after the final exam and everything, will look pretty much like what a letter grade would be at the end of our time together, but our end of our time together will be into June. So we have planned on the hands-on, some more hands-on things for everybody to have a chance to do in school during the first 2 weeks of June. Now, I haven't seen the schedule yet, what that's going to look like, but I suspect that since we normally meet on a Wednesday, that we will be there on a Wednesday at 1 o'clock for that first
Okay.
week of June, and we'll probably be there for Wednesday at 1 o'clock for the second week of June, just so that you can have some additional equipment that we're not able to do. So far, the oscilloscope has been through Multisim, which is a wonderful resource, but Multisim only takes us so far. I'd really like to have your hands on a real oscope. So we're going to have some time back in the lab. So although everybody else is final grade, so if you're taking any general ed class, yeah, if you're taking any general ed class, your English, social sciences, whatever else you're taking, separate of the sciences here, the electronic classes, then those classes will officially end this week because it's the final weeks for the rest of the school. For us, come the end of tomorrow, we'll enter the final exam scores because you're going to have the final exam score in two parts. One final exam score will be an upload that you're going to upload before the end of tomorrow's session. You're going to handwrite it, take a picture of it, and shoot it, and upload it into Canvas. The other part you're actually going to do online. So the online part will look a lot like the questions that you've been receiving all along in the review session we had last week. So just as an example, let's go ahead and do this. I'll put us on the share screen. And here, and let's go your screen 2 and hit share. And while I'm here, I'm going to go to our class and show you day.
It is the second one you sent the email.
I just have a quick question. If you want to reiterate, did you mention about printing and handwriting stuff for the finals? Is that what you said? Because I don't have any access for a printer. I mean, I can download it and work off of a Word document, but is that, I don't have an access to a printer for me to print something.
Okay, some of our friends don't. So yeah, if you don't, then you can, the document will come to you in a MS Word format. You can type in your answers.
Oh, excellent. That's good to know. Thank you.
Okay. All right. So can everybody see my share screen, see Canvas on the share screen presently?
Yes.
Okay. And if you look at week 16, we have the practice final. That was uploaded last week. And it was also sent to you all last week per Andrew's request. And it was a nice request. It was 5 pages worth. So that was attached by email also. So if you got the email to be invited to this session, then you should have received also the practice final. And this is what the practice final looks like. Right there. And we have 5 pages of stuff that we'll be going through in a little bit. But separate of that, there's also in week 16, okay, Review six chat. Let's see. There's the reply for anybody who had replied to the Canvas email in time. So this said, this was a copy of the email invite. And so it says, please reply your confirmation for 25 bonus points. You must reply. We have a Zoom meet that's scheduled for this Wednesday. And so this reply must reach me when? By Sunday midnight. So if you missed the Sunday midnight deadline, but you're still here, that's wonderful. I'm glad you're here. But the bonus points was if you had replied before then. If you didn't reply before midnight, no worries. You're not harmed. You just didn't get the bonus points. So there's the reply line in Canvas. And then in week 16, there's also, for your viewing pleasure, right here, week 16 review of week review questions. And so these are the week review questions. There's week 2 set, week 3 set, 5, 6, 7. Well, actually, this is technically 4, 5, 6, and 7. So these are the different homework questions that have come up during the course of the semester. And you can open up and look at these and as these. And where I've made notations is where previous classmates may have entered something other than a correct answer. So if we take a look at this one here, for example, back to week 2, and I go to open up this guy. And so here's an example of the question sets, if you recall. And he highlighted his answers in yellow. And so question 9 was where he had made a mistake, and I made a notation here. So for Q9, voltmeter B and D should be 0 volts. He had voltmeter A is voltmeter A 6 volts. Voltmeter B should be 0. Voltmeter C should be 6 volts because it's measuring the source. Voltmeter D should be 0. So B and D are 0. Why? When you put a meter on a bare wire, what should we measure? It's going to be 0. Why? Because there's no drop difference of potential on the wire. The wire on this black probe is the same as the potential on the red probe. That's just a piece of wire. There's nothing in between. Same thing on the switch. The switch is a wire that's just closed. So B and D should be 0, and I made a notation of that in here. And here's one that's offered by Ms. Velasquez. She did question set homework 3. We want to be looking at these guys too. Okay, so for these questions, this has to do with pressure and voltage and the graph. And so she had something here. Let's see what she put. Q5, for Q10, I had an issue with respect to Q10. Let's see what's up with Q10. Q10, oh yeah. If we short a battery, if you put a short, meaning you put a wire from one positive side to the negative side of a battery, what do you think is going to happen to your car if you do that? Your car battery might actually explode, okay? It'll create sparks and it might do something really horrible because there's a lot of current behind that car battery. If you did it with a 9-volt battery, depending upon the type of 9-volt battery, it'll also be destroyed pretty quickly. So that's called a dead short if you put a wire between the positive and negative terminals. So the question was right here, what would happen if a wire with no resistance were connected directly across terminals of a 6-volt battery? It's called dead short. How much current would result according to Ohm's law? And here's where she made a mistake. Her mistake was the current, her answer was this. According to Ohm's law, there would be no current because V divided by R equals I. The formula is correct. V divided by 6 divided by 0 is not going to give you 0. Everybody pull out your calculator right now. Pull out your calculator. Take 6 and divide by 0. And when you pull out your calculator and 6 divided by 0, Kyle, what do you get?
Is 0?
Does your calculator actually show you 0?
6 divided
It
by
gave me an error.
Yeah, mine might give me an error. You might have to do that.
Yeah, you're going to have to mute one of your microphones. You cannot have both of your microphones on. Andrew, what do you get? 6 divided by 0.
I get an error.
Error. Yeah, you get an error. Error is not a 0. Error is an error. Okay. That's not the same as 0. Pauline, what do you get when you take 6 divided by 0, Christian?
I got an error.
I got error.
Precisely. You do not get 0. 6 divided by 0 is impossible. Okay, because you do get an error. In fact, what it comes out to is there would be infinite resistance, infinite current rather, on a dead piece, on a 0 resistance wire put across a battery. There's so much current that flows at that moment. It is infinite resistance. And depending, like I say, depending on the type of battery, it could burn up, it could melt. It may not explode, but it will certainly burn up. And it might leak depending upon whether it's a carbon battery or not, but it will not be 0. So what I wrote down here is note for Q10, current initially will be infinite before the battery what? Burns out. Separately, there's a separate question. What would happen here? Suppose you were to short circuit that 6-volt battery in the manner described, and you measure 8 amps of current instead of infinite. Why don't the calculated figures from the previous paragraph agree with the actual measurement? We put here with 0 ohms on a wire shorting this battery, we would have infinite current, and then the thing would blow up. Here, they're saying, suppose you're able to actually measure 8 amps of current. If you're able to measure 8 amps of current, so let's see what they say here. So she put down, yeah, the actual measurement does not agree with the calculated figures because there's the internal resistance in the battery. Now, her figure is wrong. It's not 0.75A because there's no A. The 8 amps is the A, but there is an internal resistance. So here's 2 possibilities: high internal resistance of the battery and or high resistance in the short. So those are 2 possible answers for question number 10. Otherwise, the rest of the answers for all the rest of these look to be correct. So if you wanted to review those chapter questions, you may do so. They are there for your viewing pleasure. Any questions about all the chapter review questions? So your online final will be similar to this type of question set. Okay. Okay. Next, let's go ahead and close this guy out. Let's take a look at our practice. Okay. So on the screen share, let's go ahead and do this. So first question goes to Pauline. What do you think? Read the question and think, state what you think the answers should be.
In the negative electron current model, from negative side to the positive side of the voltage source will be the direction of the current flow. Is my answer.
Okay, negative to positive. Oops, where'd that come from? Negative to positive. And we'll highlight. Oh, That is correct. And conventional current model, question goes to Andrew.
It would be positive to negative.
Positive to negative will be correct. Okay. Let's go ahead here and here, here, and here, and there. Okay, so that would be correct. And question number 3, the subatomic particles that exist within the nucleus of Bohr's model of the atom, that would be what, Kyle?
Protons or neutrons?
Protons and neutrons would be correct. And the subatomic particles exist outside the nucleus of the atom. Christian?
I'm not sure, but I would have to say electrons.
Electrons would be correct. They exist outside the nucleus. They're still in the atom, but they're outside the nucleus. Okay. And Pauline, question number 5.
Protons are the subatomic particles that are positively charged.
Protons would be correct. Okay. And Kyle, number 6.
Electrons.
Electrons would be correct. And Andrew, number 7.
Neutrons.
Number 7, neutrons would be correct.
Can Kyle just log off and just use this with me so that we don't get that echoing?
Yes, but I wanted to make sure that before he logs off, Kyle, can you switch on your camera? Okay, and Andrew, switch on yours. Everybody switch on your cameras for a moment. Okay, so this is a camera check. So camera check. All right, so this way we don't have any rude surprises come tomorrow. So it's good that we're able to get this done. You can see me, I can see you. So we would be all set for tomorrow. So yeah, so from this point on for this session, Kyle, you can log off and just sit in with Andrew. All right, thank you very much. Okay. Let's start with number 9, and then that'll help you with number 8. Starting with number 9, Pauline, what do you got? Random charges, not type of electricity where you have random charges not flowing in a circuit.
That's a good one, because I didn't answer that.
Okay, somebody want to volunteer this?
I thought it was an AC circuit.
No, not flowing. See, AC has current flowing. So in AC, current flows back and forth. It flows part of the time one direction, part of the time in another. So that's what AC. So AC is current that is flowing. Here we're talking about a type of electricity for charge. You have charges, but not flowing in a circuit. So here, let me give this to you. It's called static electricity.
Oh, okay.
Remember static electricity, you know? That's the type of electricity, the snap, crackle, and pop that you hear when you pull clothes out of the dryer that have not had the static guard put in. So if that's static electricity, then this one would be dynamic. Okay, okay. All right, number 10, question goes to Christian. The most common method of creating static electricity.
I know you get it from rubbing on stuff. But...
Okay, rubbing is perfect. That is correct. It's actually called friction. When you're rubbing one fabric upon another, you're creating something known as friction. So that's one of a number of freeing static electricity. There happens to be at least 7 different ways of freeing static electricity. Do you remember what those other methods were? Also, so there would be heat. Also, we have heat. Electricity itself would create this.
Magnetism?
Yeah, I'm thinking about freeing electrons. So here, maybe I better phrase it this way. Reminder, we can free electrons via heat, electricity, apply magnetic field, light, or your solar panels, friction, chemical, and pressure. So there were 7 different ways of freeing electrons, and friction is the most common one for creating static electricity. So Gabriel, welcome. So glad you could join us. Let's do a camera check on your machine. Okay, good. Yeah, all right. We just want to do a camera check, make sure we're good, because tomorrow we need your cameras working. All right. So now we're on question number 11. So question number 11, question goes to Andrew. What is
Current.
defined as the pressure to move electricity?
Current.
Pressure. How would that differ from question number 12? Question number 12 defined as charges in motion. So charge in motion would be current. You want to think of something flowing. Current is your charges in motion. It's either direct current or alternating current, but that's your charges are actually in motion. So current would be the best answer for number 12. The pressure to move electricity would be analogous to voltage. Voltage is the pressure. You have 120 volts at that wall outlet, you got a lot of pressure there. You got a 9-volt battery, you don't have as much pressure in the 9 battery. Follow? Okay,
Yeah.
so think of voltage as being analogous to pressure. Think of current as charges in motion. So Kyle, what is this defined as the opposition to the electricity flowing?
Okay. AC circuit?
The opposition to electricity, what opposes the flow of electricity?
The resistance?
There
Resistor?
you go.
Yeah.
Resistance. Yeah. Okay. Okay, so the next question. Gabriel, can there be electricity flowing without a voltage source?
Yes.
Without a voltage source,
Oh, without a voltage source, no, sorry.
can there be electricity flowing?
No.
It would be a no. Okay. You need a voltage source. You need that pressure, otherwise there's no electricity flowing. Can there be voltage without electricity flowing? Question goes to Pauline.
Originally I answered no, but I guess this would be a yes now at this point.
No, why would it be a yes at this point?
I don't know. I had to think about it last night and I was like really convoluted, but I guess my answer is no.
Well, here you go. You have a 1.5 volt battery in your hand. Is that 1.5 volt battery a voltage source? Yes, it has 1.5 volts of pressure to move electrons. So does that battery represent a voltage source? The answer is yes.
Yes.
So can you have a voltage source in your hands, but no electricity is flowing because there's no
That
wires
makes sense.
attached?
Correct. That makes sense now. So,
Does that help you understand the answer
Yes.
being yes? So yes, you can have the pressure without the flow. You just don't have it connected to anything. Now this one here was missing an underline, sorry. So if we put the underline in here, omega represents what electrical quantity? Question to Christian. Mr. Cortez?
You hear me?
I can hear you now.
Oh, it would be the ohms or resistance.
Okay, it would represent the electrical quantity resistance. Yeah, the ohm is the unit of resistance, but the quantity is that we're looking for is the resistance. Okay. All right, so here we go. These are really good questions. If voltage remains the same, what will happen to current if the resistance is doubled? So the best way to play with these guys, is to just hypothetically, let's put in some numbers. Let's say if V equals 20 volts and R equals 10 ohms. Calculate the current for that for me, if you would, please. Everybody, V is 20, R is 10. Calculate the current.
Okay.
Who shouted out what answer? I'm sorry.
Chris, 2 amps.
Yeah, so what current did you calculate?
2 amps.
Yeah, so I is equal to 2 amps. So you give yourself a hypothetical starting point when you're faced with this type of question, okay? So here's a starting point. You got simple numbers. Voltage is 20 volts, R is 10 ohms. Can you calculate the current? Yes, you got 2 amps, all right? So now what they say, resistance is doubled. So now if V equals 20 volts, R is doubled to 20 ohms. So now I is equal to what? So look at the numbers. Did voltage stay the same? Yes, voltage remains the same. It started off as 20 volts. I have this at 20 volts. Resistance is doubled. Well, what was it originally? It was originally 10 ohms. It is now 20 ohms. So now I have a new circumstance. 20 volts, 20 ohms. What's my current? Question goes to Kyle.
1.
One what? Current is measured in what units?
Amp.
1 amp. Perfect.
Yeah.
Right. Is everybody in agreement with the math? I is now equal to 1 amp. So how has the current changed? How would we answer this question, Andrew?
It went down by half.
Okay. Can we say halved? One word?
Yeah.
Current halved. Okay, because of this scenario. So when faced with this type of question, is it easy for you to generate your own scenario numbers like I just did? Are these easy numbers? Start with some value of volts, start with some value of ohms, calculate a current, then stay with the voltage, show the resistance being doubled, and then recalculate current. Does everybody follow how easy this was? So now let's see,
Yes.
we're going to do the same thing. Number 17, if resistance remains the same, what will happen to current if voltage is doubled? Well, so now V equals 20 volts. This is originally 10. And R remains the same. R equals 10 ohms. So I equals blank. And let's see if this is correct. Remember our original scenario. This was our original scenario here. I'm going to color this in blue. Our original scenario had 20 volts, 10 ohms, 2 amps. So it says resistance remains the same. That's 10 ohms. And the circumstances, voltage is what? Doubled. So voltage, I'm going to make this 40. Okay. So now does this voltage show a doubling from the original 20 volts? Or is our resistance the same? So what will happen to current as a result? What's my current? What's this calculate to be?
It'll go up.
What's it calculate to be?
Oh, 4 amps.
It will calculate to be 4 amps. Okay. So up will not be a good enough answer. What happens?
Increase.
Be more specific. Increase is the same as go up.
Double.
Be more specific. Compare your 2 amps to your 4 amps.
It'll double.
That's the word we're looking for. Doubles. Wasn't the original 2 amps right here? And do we now calculate 4 amps? So if you just simply say increases, if you simply say go up, that's a partial answer. That'll get you partial credit. But if you say doubles, that's very specific because it tells you how much it increases, how much it went up by. Everybody understand how to better answer that question? Okay. Now, third scenario, if current remains the same, voltage must be if resistance is doubled. Okay, so now, if current remains the same, so I is equal to 2 amps. That was our original. And resistance is doubled. What was my original resistance? In blue, 10 ohms. So I double that. What's my new resistance? Are you all on mute? I'm looking for some collective responses.
20 ohms.
20.
20.
Okay, so we type in 20 ohms. So V must calculate to be what? Do the
40,
math, and I'll
40,
call out a
40
name.
volts.
It's I times R. So this works out to be
Ohms up.
40 volts.
40 volts.
You're right, 40 volts, correct. And so what word do we use here? From the original to the present. What must happen to the original voltage in blue to give us this current voltage to meet this scenario?
Voltage must double as well if resistance is doubled.
Must be doubled, correct. There we go. Okay. So just simply saying goes up, goes down, increases, decreases is not enough. Does it go up by 4 times? Does it go up by 2 times? Does it go up by 10 times? You have to be specific, okay? Okay. Voltmeters must connect how in order to measure voltage? And I put down in parentheses, it's either going to be parallel or in series. And so question goes to Christian.
Would it be series? I mean, parallel? Because
This,
isn't series like if like the way you showed us right now that it was in the same wire?
yes.
Need anything?
Yeah, so in the example that I showed you previously, yeah, so it would be in parallel. So parallel is correct. Meaning it's across the component that you're looking to measure. And then ammeters must be connected, in this case, in series. Right there, right there. Everybody okay with that?
Yep.
All right, number 21. Gabriel, what do you think about this? 21.
I believe you could. You could get an electric shock. I say is yes.
Read the question. Yeah, read the question all the way through.
You get an electric shock by contacting a single point.
Mm-hmm. Okay, can you get an electric shock by contacting a single point?
I said, I don't think so.
Yeah, by contacting a single point, it would be difficult. It can happen. It's not as likely to happen. The key thing about electrical shocks is you're definitely going to get an electrical shock if you contact at 2 points. Remember, voltage is always measured between 2 points, and current flows between those 2 points. So for example, if you were standing in a puddle of water and you had your hand in the electrical socket, well, you're completing the circuit because the electricity is flowing in your hand through your body, down through your feet to where you're standing in water, and your shoes are probably wet and probably not insulated galoshes or something. You will get shocked. If, however, you're standing with on dry ground and you're standing with well-insulated shoes and you touch something electrical with one hand, you're not as likely to get shocked by touching a single point. Now, that doesn't mean you still couldn't get shocked because you're grabbing with 5 fingers. If you go to touch it with 1 finger, it's less likely you're going to be shocked. So can you get an electrical shock by contacting a single point? The answer would be not likely, okay? Closer to no than not, so not likely. Yeah, wrong place. Let's put a no for the time being. All right, so now how about this? Your GFCI wall outlet will trip when? When will your GFCI wall outlet? Who else? You all have bathrooms. If you look at the wall outlet in your bathrooms, you'll see it's marked GFCI. What does GFCI stand for?
Ground fault interruption. Circuit interrupter. Ground fault circuit interrupter.
Right. When will it trip?
When current goes somewhere else besides back to the GFCI.
Mm-hmm. It's there to protect you when
In 5 milliamps or something like that.
unintentional. Well, it's very little,
Yeah.
and it's very quick. So here you go. Unintentional. If there's an unintentional short to ground, then that thing will trip and cut off the circuit and therefore save you from being electrocuted.
But if
Okay.
it pulls too much power too, it'll trigger it also, right?
It is, you can also, if you pull too much power to it, it should have the same rating as your circuit wiring. So your circuit wiring on most of those is at least 15 amps, if not up to 20 amps in a household. So if you run more than 20 amps, if you exceed the wire rating, then the circuit breaker trips. But the GFCI should not. The GFCI should hold and let the circuit breaker do its job. So
Okay.
so that's what your circuit breaker is for. It behaves like a circuit breaker in that if there is an unintentional short to ground, then it will trip. But if there is an overcurrent situation, like you're drawing, you hook up all your Christmas lights for some reason to that outlet, and you're drawing well more than 20 amps, then your circuit breaker should trip, not the GFCI, because they're designed to do two different things. The regular circuit breaker in your wall panel is a circuit breaker. This behaves like a circuit breaker, but they're designed to protect your house wiring differently. This is not designed so much to protect your house wiring as much as it is designed to protect you from being shocked. That's what the GFCI in your bathrooms and your kitchens are primarily there for. But your circuit breakers in your wall panel are designed to keep your house from burning down, to keep the wires from heating up to where they melt and catch a fire and cause your house to burn down. So if you have too much current, that's the job of your circuit breaker. Okay.
Okay.
Okay. Number 23. What prefix should we be using here, my friends? Shout it out.
Milliamp.
Okay, so this would be M, which is equal to milli. So that's the prefix. How about this one here? What is the symbol and how do we speak it?
It's picofarads.
Pico. How the mouse goes where it does is a mystery to me. Pico. Boom. This has no relevance. Okay, and then what power of 10 is the U associated with, Gabriel? This little U. What power of 10 is that associated with?
The micro?
That's how we call it, but what is my power of 10?
-6.
And so this is what you got to do. You show this as a 10 -6. So if you put this down, if you write down the word micro, M-I-C-R-O, that would be wrong. Because what is the question asking us for? Right here. Exponent. Exponent.
How did you get that exponent up there like that?
I'll show you with the next one.
Okay.
So G watts is associated with what exponent? 10 what power?
Giga.
+9.
10 what power?
10 to the 9th.
Okay, so you 10 to the 9th. All right, so you type in a 109, you highlight the 9, and then you come up here to home, and right here, these two, you can make it a subscript, you can make it a superscript.
Okay.
Subscript like H2O, superscript like square or powers. So if I do this, I now have 10 to the 9th power. So that's done.
Thank you.
You're welcome. So understand, if it's asking you for exponent, do not say giga. Yes, G is giga. This is gigawatts for sure. But if you type in giga, giga does not answer the question. The question was exponent. Okay. If however, it's phrased, what is the metric prefix? How is the metric prefix spoken? Then you would type in GA. Are we clear on that for number 26? Number 25, are we clear that this little u, which is the exponent 10 power -6, if you were asked for how this engineering prefix is spoken, then and only then will you write down micro, okay? But if you type in micro for this number 25, that would be wrong. Number 27, can you be electrocuted in pure water?
No,
Why?
because there is no minerals and stuff in it to carry the
Exactly.
electricity.
You got it. No minerals, no electrolytes, precisely. Okay, so this particular question, blank is the current in a circuit with a 5K potentiometer adjusted to its midpoint with a 10-volt source. How do you approach this particular exercise? Question goes to Kyle.
For number 29?
28.
Oh, no, you can't be electrocuted in pure water.
No, 28.
Yeah, you're because our number 28 is the water thing.
Our numbers are off.
Yeah, our numbers are off. You're missing something in here.
Nah, it's just his numbers, we're one ahead, so just
Oh, okay, so we're on 29.
yeah, he's on 28, we're on 29.
Yeah.
I don't know why it's like that, but that's how it shows on our paper.
That's interesting. Number 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 16, 17, 18, 19.
You're missing
So
20.
go back to your first page.
Oh, that's 20.
Is 20 at the top of my paper and it says ammeters must connect in series? Or did
No,
I miss a question somewhere?
That's
See,
20.
that's our 21.
What's your question 20?
Voltmeters must connect in parallel.
What's your question 19?
If current remains the same, voltage must be doubled.
What's the next one down? So
Uh,
look at my paper. See, tell me which one you see on your paper that I'm missing on mine.
12. You're missing the
13. 13's different.
the resistance is defined as an opposition to electricity. You don't have that.
Jesse, when you highlighted that, it deleted itself. You might have highlighted
Oh, okay. I see what
right there.
happened. Okay. There. Okay, so now we're back in sync with each other,
Yes.
I hope. Yeah. Okay, there we are. All right. Okay, so question 29.
For question 29, I wasn't.
Gabriel?
Yeah.
Yeah, what do you think about 29?
Current circuit with the fun.
How do you take the facts of what you're given
Uh-huh.
and apply Ohm's law to calculate current? What facts are you given? V is equal to what?
Voltage 10 volts.
10 volts. Okay, so we write down 10V, comma. What else is given? Are you given ohms?
The resistance,
The resistance is equal to,
5 kiloohms.
what's it say about resistance? It's a 5K ohm pot, but where is it adjusted to?
with the 10-volt source.
No, what's it adjusted to?
Oh, to its
Read
mid,
the rest of that line.
to its midpoint.
So a potentiometer, yeah, so if you take a potentiometer, remember, we had a potentiometer lab. We did this weeks ago. When you take a potentiometer, what is a potentiometer? A potentiometer is a variable resistor. You can change it. So it has 3 terminals, okay? So if you take a potentiometer and you adjust it from 5K to its midpoint, how much resistance should we have? What's the middle of 5K?
2.5
2.5 what?
kiloohms.
Okay, 2.5 kilo ohms. So if you recall, let's just bring this guy up. Okay, I bring this guy right here. You can see, here's your potentiometers. We played with this. And you have 3 terminals, and you can adjust by turning this knob. So by turning this knob, you can change the amount of resistance. So here is the potential. Here's another picture of a potentiometer. So we can change by moving the wiper. The wiper is attached to the knob, and we can rotate it from one side to the other. And then so pins, the outside pins are your 5K ohm pins. We're measuring from one outside pin to the middle by adjusting this. So if we adjust the 5K to its midpoint, so from the midpoint to the variable end, so between these 2 terminals, a fixed end and a variable end, we should have 2.5K. Does that joggle everybody's memory of how a potentiometer works?
Yes.
So my R in this case would be 2,500 ohms. 2,500 ohms. So now do I have enough information to calculate current? What do I do? I is equal to what? You should all have your notebooks open. You should all have
4
Ohm's
million,
law in front of you. You should all.
4
So
million
how do I do this? Okay, what's my formula?
V divided
I
by
is equal
R.
to what? I will be equal to V divided by R, precisely. And so what is my V in this case? My V is 10. What is my R in this case? 2,500. Do I have enough information to do this?
Yes.
Okay, what's it calculate to be?
Or 4 kiloamps. 4 kilo ohms.
Be
We're
million.
looking for current, so we better know our units and we better know our engineering.
4 milliamps.
Mm-hmm. So the units are of current are amps, not in ohms. And 10 exponent negative 3 is a milli, not kilo. So you've got to watch out for how you go about answering these word exercises. You got to know your engineering prefixes, and you got to know your physical quantities. It's not ohms, it's amps. It's not kilo, it's milli. Are we good with this? And everybody understand why? 4 milliamps. Now, here you go. It's asking you, what is the resistance of a potentiometer in a circuit if you have this circumstance? So how would you approach this one, Pauline?
On this one, I had to do an R3, which is 75, and then I had to do and I think my final answer have 31.
So for number 30, if the resistance of a potentiometer in a circuit is 15
Oh,
volt source
I'm
and
sorry.
10 amps is
We're on
flowing.
number 30.
Yes.
Yes, my
Yes.
answer is 1.5 ohms. So given that I have 15 volts and 10 amps flowing, so my R will be R equals V over A, which would give me 1.5 ohms.
Yeah, R is equal to V over I, which would be 1.5 ohms. Correct. Cool. Everybody okay with this so far? Okay, and I think this one, oh, this carries over one. So let me do this. That's all right. Change anything. Okay, so Christian, how would you approach this particular exercise for number 31, 2, 3, 4, 5, 6? How would you approach this particular one? Christian?
You could use voltage divider formula. Are we looking for voltage? Let me read the complete answer. I mean the questions. It'll be the measured voltage.
Well, you're given the circuit, and the circuit is shown 75 volt source. You have 3 resistors. And so the following questions pertain to this. Blank would be the measured voltage if the red probe is connected to the bottom of R1 and the black probe is connected to top of R2.
Okay, then can we figure out like the total resistance and then figure out the voltage drop across the 3 resistors?
Well, you can do a complete circuit analysis. This particular question is the red probe at the bottom of R1 and the black probe connected to the top of R2. So in this particular case, let's go ahead and pull this particular guy out. And you don't have to do any math on this one at all for number 31 or 32. And let me explain to you why.
It'll be 75 volts, no?
You think so?
Well, yeah, because the bottom of R1 is basically like the bottom of the battery to the negative, and then the top of R2 is basically across the whole the whole circuit. So it'll be the difference between the whole circuit, which is 70.
I like the way you think. You're kind of on the right track. Does anybody else have an agreement, disagreement, comment?
I mean, what he says kind of makes sense, but I don't know. I mean, I see exactly what he's saying and where it is, and it doesn't cross anything. But the negative has to cross through those, I believe. But he's picking the negative up on one. I see what he's saying.
So what do you think the voltage? What do you think would be the measured voltage?
Negative 75 volts.
Negative.
Yes, it would be. It must be negative 75 volts.
Yeah.
Negative 75 volts. Okay, so here's what's up with this, and I'm going to take a moment and redraw this particular circuit. Let me get a focus on my camera first. So let me switch the source, stop the share, and then come to here. go to the camera. Okay, we can see this. All right, close enough. So what we happen to have here, my friends, is this. We have a voltage source. We have a resistor. And then over here we have two resistors. And this is given as 75 volts. This is R1. This is R2. This is R3. And if you polarize this, if you recall how we polarize things, let me go to speaker view. Can everybody see this better? All right, mute your microphones for a moment, please. Thank you. So if we go to speaker view, what it is that you see, positive up here for this part of the source, negative here, which means everything attached to the positive will share its polarity. So this side is positive, this side is positive. Everything attached to the negative will share its polarity. This will be negative, this will be negative. So between R2 and 3, this will be positive, negative, positive, negative. That's how the polarity will go on these resistors. And the first question goes to ask you, red probe is connected to the bottom of R1. Right there's your red probe. Black probe is connected to the top of R2. There's the top of R2. Isn't the top of R2 the same as the top of R1? Aren't they electrically the same point? Yes. So having the black probe here at the top of R2 is the same as having the black probe at the top of R1. And isn't that wire also extended to the top of the voltage source? So that means it would be the same as if I put the black probe up there. My red probe here, because this is all one wire, would be the same as if I put my red probe here. So what I've got, my friends, is a voltmeter. Here's V for the voltmeter, and a black wire attached there. And I've got the red wire attached here. So when I'm going to measure, not only do I measure 75 volts, I will specifically measure negative 75 because the red lead sees negative, and it's always the red lead's polarity of what it's connected to is what determines the polarity of your voltmeter reading. So the answer to question 31, number 31, 31 is equal to negative 75 volts. Is everybody okay with that answer and understand why? Okay, so the next question, number 32 is asking, what is VR1 calculated to be? Well, VR1 is the voltage here. So when we're asking for VR1, VR1 doesn't specify any particular polarity how we're going to measure it. We can measure it with the red lead on the bottom. We can measure the red lead on the top. This alone does not specify how we measure how we place the red probe. So this is simply answered as 75 volts with no polarity. How we measure VR2 and the rest of these depends on how we simplify this circuit. So what we're going to need to do is this 50 ohms, this is 35 ohms, and this is 40 ohms over here. You are asked for a couple of questions, VR2. So what is my voltage across R2? Here is where you would use, so for number 4, number 33, which is asking for VR2 calculated. I would suggest, you could do a number of things, but I would simply suggest use voltage divider formula, VDF. We know how much voltage is at between the top and the bottom, 75 volts. This branch is in parallel with the source. These two resistors form one resistance in parallel with the source. So do I know the voltage from the top of the volt source to the bottom of the source, how much voltage do I have across these guys? Across these guys, I've got from here to here, 75 volts, because those two guys form a single resistance, which is in parallel with this voltage source. I have 75 volts across two resistors. Can I use voltage divider to find what's across one of them? Yes, if you recall voltage divider formula, isn't that nothing more than VRX is equal to RX over RT times your voltage source. In this particular case, this will be 35 ohms. But RT, is that RT for my entire circuit, or is that RT only for what's happening in this branch? Question goes to Gabriel. What do I use for RT? Gabriel. Pauline. Andrew.
Our
I think it's just that branch.
Okay, so what would my RT be?
Your RT would be 75 ohms.
75 what? Apples?
Ohms.
Okay. All right, 75 ohms is correct. And my voltage source is 75 volts. So that's my voltage divider. My voltage divider only applies to what's in series, okay? Voltage divider is used only for series circuits. Current divider is used only for parallel circuits. So if I want my VR2, I will use the value of R2 over the total ohms of what these two are in series. So can we do the math? 35 divided by 75 times 75. What do I get?
VR be 35 volts.
35 volts. Cool. Everybody okay with that? Now, you're asked for RT, so number 34. RT is equal to question mark. So how would we solve for R total for this particular circuit? When we have combinational circuit, we look at the circuit from the farthest away from the voltage source. Voltage source is here. Here's the point farthest away from the voltage source. So as I look back, we determined that R2 and 3 have what relationship to each other? They were in series because they formed the voltage divider, which allowed us to use voltage divider formula to calculate the previous voltage. So could we not show this way, where we have an R1 that was 50 ohms, and then over here we have a single equivalent resistance called REQ1, which was equal to R2 in series with R3. This was equal to 75 ohms. Is that correct? Could we take the 3 resistors and simplify this down to 2 resistors? And now can we simplify this further in order for us to find R total? What is the relationship between this branch and this branch, the 50 ohms in relationship to the 75? What is their relationship? Question goes to Andrew.
What was that again?
What's the relationship between R1 and REQ?
They're parallel.
Okay. If they are in parallel, how do I calculate these two guys to a single total resistance?
You times them, right?
Parallel with 75 ohms. So we have several methods by which we can calculate this. We can use reciprocal method, We can use product over sum. So let's go ahead and use reciprocal method. So that would be 1 over 50 plus 1 over 75 equals, and then your reciprocal one more time, okay? So how did we enter this into the calculator? It would be 50, and then you find your reciprocal key, x negative 1, and you add that to the 75, and you hit your reciprocal key, x negative 1. You hit equals, you hit the reciprocal key one more time, and you hit equals one more time. And so when you go to do so, what calculate, Pauline?
RT is equal to 30 ohms. RT calculated to 30 ohms.
Okay, so how many people agree this works out to be 30 ohms?
Sounds right.
Okay. Okay, so that answers question 34. Once you have 30 ohms, so RT equals 30 ohms, and we write this here, do we have enough information between voltage source and 30 ohms in order to calculate current? Can we calculate IT? So number 35, IT is equal to question mark. So based on these two guys, according to our friend Ohm's law, V, I, and ohms. How do I calculate I? I would be equal to V divided by ohms, yes? Isn't this equal to 75 over 30 ohms? So what does this calculate to be? Question goes to Kyle.
2.5 amps.
2.5 amps. How many people agree?
Yeah.
Sounds good so far, yeah? Pretty good. Pretty good. Okay, so, and the one down below is IR1. How much current flows through R1? So who would like to describe what happens there?
You'd have to use current divider formula.
Current divider formula. I like current divider formula. And so, number 36, IR1 equals question mark. So in this particular case, use CD, and CF is current divider formula. Current divider formula. So if we go to use current divider formula, I would submit for us to use this middle redraw. We had the original circuit of 3 resistors. We redrew that, simplified it down to 2 resistors, branches. And why don't we go ahead and use this drawing? And so here we know that our IT coming out here will be 2.5 amps. And when it hits this node, part of it will split to go up, the other part will continue and split to go up here. So part of it goes up a 50 ohm branch, part of it goes up a 75 ohm branch. You need to use current divider formula. So CDF, if you recall, was IRX is equal to RT over RX times I total. So there's your current divider formula. And how do I pop the numbers in? What number do I use for R total? R total would be the total of 2 guys in parallel. Wasn't the total of these two guys in parallel, my R total here of 30 ohms. So this would be 30 ohms. And then if I want current through R1, then I have to use the value of R1, which is 50 ohms, and times my 2.5 amps. Do I have enough information here in order to calculate my IR1? So my IR1 mathematically calculates to be what? Andrew, do you have that number for us?
Working on it.
Okay, so you
Well,
worked on it. What's
1.5.
1.5 what, apples?
No, amps.
Ah, there you go, see? 1.5 amps. That would be correct. Any questions on number 36? Number 30, whoops, did I skip one? That was number 37 for IR1. How about the number 36, which is IR3? How would we calculate IR3? So IR3 is equal to RT over, R3 is in this branch, yes? And isn't R3 part of the 70 ohm branch? R3 is the 40 ohms when combined in series with the R2 35 ohms. These two guys combined to give us 75. So if we can find the current on this side, it is the current that flows through these two resistors. So it would be RT over REQ1, which in this case is 30 ohms. In this case, over 75 ohms times 2.5 amps. So this is my IR3, which is the same as my IREQ1. What does this calculate to be? Question goes to Gabriel.
At 1.0 amps.
Works out to be 1.0 amps. Okay, does that make sense to you all? We calculated 1.5. We calculated 1.5 amps here. Different. Okay, we calculated 1.5 amps here, 1.0 amps here. The 1.0 amps comes along here. What happens when it combines with 1.5? The 1.5 is coming up, the 1 amps is coming here. What happens when they combine at this node? What do they add up to be, going back to the source? Do they add up to the 2.5 amps that originally came from the source? The answer is yes. So this is a good check, and this is a good check. Another good check is this. Do I have appropriate distribution of my current? In other words, does the higher ohm branch have lower current? Does the lower ohm branch have higher current? Is that proportional distribution of the currents? The answer to that question is also a yes. Does help to answer your questions from number 1 through number 37. My friend.
Yes.
Okay. Okay. So let's go ahead and take this information back over to here. Now, I've got to say this. I sent this out. I created this and I sent this out at Andrew's request, which is a really wonderful request. Thank you very much for asking for this. And I sent it all to you with enough time for you all to do it. And not everybody has done this, which is concerning, because if you're hoping to just sit here and get answers from me as to how to solve this, this is some learning, but it's not as good learning as if you tried to do this on your own. Say, oh, I tried this, I didn't quite use the same approach or something. And your understanding is going to be elevated if you had done the work. You follow what I'm saying?
Yeah.
Yeah. Let's try to keep that in mind in your future classes, whatever classes that you do take. Is you want to be more proactive about your education. You want to be more proactive about what it is that you're doing in terms of the opportunities given to you. Had Andrew not asked for this, it would not have been generated. I didn't have one generated before. Not that it's not a good idea, it's a great idea. But since he did ask for it and it was generated, then it would have been great if everybody had done this ahead of time as thoroughly as possible. That way we're not sitting here waiting for your calculations to be done or you to be thinking about this, but actually, yeah, I calculated this because of blank, blank, blank. Okay, any questions on this exercise? Okay, so now those answers are filled in on the answer sheet. The answer sheet alone doesn't begin to explain what it is that we have in front of us right here. So the next question on your sheets shows another circuit, and this other circuit has a bunch of questions, values to be calculated, and things to be determined. So I'm going to draw this other circuit for us. And so here we're starting with a 25 volt source, and we're given a single resistor and then a pair of resistors. So this is my R1 of 38 ohms. R1 of 38 ohms, and R2 and R3, 20 ohms and 30 ohms. All right, so I think the best thing to do is let's just go ahead and simplify. Simplify. How? Via redraw. All right, so what are we going to redraw? Andrew, what do you think? How am I going to take 3 resistors and bring it down to 2? What relationships do you see?
I see parallel.
Between what and what?
R2 and R3.
Could we simplify those into a single resistance?
Yeah.
And what would we label that single resistance to be?
REQ.
REQ1, that's good. And that is my R2 in parallel with R3. And here's my R1, that's 38 ohms up here. So are we good with this so far? Is that's the methodology you're thinking about? Did I draw out what you were thinking?
Yes.
Okay, so that means we happen to have 20 ohms in parallel with 30 ohms. And again, you could do product over sum or you could use reciprocal. So let's go ahead and calculate an equivalent resistance for these two in parallel with each other. Go, everybody. 20 parallel with 30. So I would, on my calculator, in real time, take 20, hit reciprocal, add 30, hit reciprocal, equals reciprocal equals. There, I have an answer. What do you have?
12 ohms.
This works out to be 12 ohms. for REQ. Everybody okay with that? And then from here, could we find a R total? So I have 25 volts, and I were to simplify this into one more. Let's see what this would look like. Doot, 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 doot. Let's call this R total. So here I happen to have a 38 ohm. In what relationship with REQ? These have what relationship to each other, Kyle? These two right here.
Series?
Series. So what would my total be if I have 38 series with 12 ohms?
50.
50 what?
50 ohms.
50 ohms, precisely. So 25 volts. Do I have enough information here to calculate an I total? Class, according to my friend Ohm's law, which I'll remind us over here since it's a nice space, V, I, and ohm. Do I have enough information here to calculate current? Current would be equal to V over ohms, yes? 25 over this. So my I total is going to be equal to 500 milliamps. Is that correct? If your calculator's left in the decimal mode, it should show you as a 0.5. If you've got 0.5 on the display of your calculator, you need to reset it into engineering so you see 500 milliamps. So far, so good?
Yeah.
Okay.
This
So
is
I'm
what
gonna-
confuses me is I get it down this far, but then I don't know exactly what box to put everything in. So when I
Well-
start getting my numbers here, I don't know if it goes in IT, RT, or IR1 or whatever. This is where I
I
get
got a
have
great-
I have a good solution for that, Andrew, because at first it's a little confusing looking at the paper, but when I did our little table thing where R1, R2, R3, and then the VIR, that's what I did to plot down all the numbers, because then, you just work your way up like we did in all of our exercise. And then in the end, then you can plot down your answers.
Okay.
Did everybody understand what Pauline was suggesting?
Yeah, she was suggesting that I put a chart on there with the V on top, I, and then the R.
Precisely. We've done this a lot of times. So we will do a V, we will do an I, we will do an R, and we will do this for 3 resistors. Our friend, the VIR chart, never goes wrong. So you have one row for R1, one row for R2, one row for R3. You have a total row. And you have 3 columns, like so. And in the R, you have 38 ohms. That's a given. You have 20 ohms over here. That's also given. You have 30 ohms. That's given. And you have a 25 volt source. That's also given to you here. And now the thing is to fill in the rest of this chart. Once you fill in this chart, then filling in the answers on the question sheet should fall into place fairly easily. If you look only at the questions on the answer sheet in the absence of this chart, it'll be harder for you to determine. It's not something you could easily eyeball. But if you set up the chart, this allows you to set up your analysis in a very organized fashion that we've done many times over. So what's the first thing we need to determine to fill in this chart? We've already started doing this. What have we determined so far?
That R2 and R3 are parallel.
Yes, and they gave us an equivalence of 12 ohms. And what that's important to know, but that doesn't fill in anything on the chart yet. What else did we do once we calculated these two guys in parallel, giving us 12 ohms for EQ1? What else did we do?
Then we added it.
We added those two, and when we added those two, we ended up with a very nice total ohms, did we not?
Yes.
So perhaps we can write the total ohms in here as 50 ohms. How about that? So far, so good?
Yeah.
All right, what else did we also do in this very simplified series circuit? We also calculated what? An I total. And the I total calculated to be 500 milliamps, yes? And we could do that on our chart as well. In any row, as long as you have two quantities, you can always calculate a middle missing quantity. So you have 25, 50 ohms, you calculate, so it works out to be half of an amp, which is 500 milliamps. Are we in agreement with that so far? Okay, so
Yes.
here's the next question. So the next question to the group, if I found one current, have I found all the currents? Can I take this and fill this all the way up?
No.
No, but you could do it for number one.
I have 25 volts. Can I take 25 volts and fill this all the way up?
No.
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 So I cannot take the 500 milliamps and fill that all the way up because this is not a, the whole circuit is not just a series circuit. So I cannot do that. I can't take the 25 volts and fill in the entire voltage column because the whole circuit's not a pure parallel circuit. But what I can do with the 500 milliamps, and Christian is correct, I can take that 500 milliamps, which flows from here, up to here, over to here. I can take that 500 milliamps and apply it to the intermediate circuit right here. I have 500 milliamps, and it's flowing up through the equivalent, and it's flowing up through one of my original circuit resistors. Whoa, I now know this 500 milliamps is in fact flowing through my R1. I can fill this in right here. 500 milliamps is indeed there. What do I do to find the currents here? I submit that.
Don't you just divide it in half? The 500 milliamps?
Then I would have 250 and 250, correct?
Yes.
Could I divide it in half?
No.
Should I divide it in half?
No.
Are these
No.
ohms the same?
No.
I clearly have a split. For sure, I have 500 milliamps coming down here, and part of it splits up here, part of it continues and split here. Do I have an even split? I do not have an even split. I cannot split this to 250 milliamps and 250 milliamps. Why? Because I don't have equal number of ohms. I have more ohms on this side, less ohms on this side. So remember, more current will flow through less resistance. Less current will flow through where there's more resistance. So what should I do at this point?
We used the current divider formula.
Use current divider, CDF. And specifically, my IR2 is going to be equal to RT over R2 times I total. And my IR3 is going to be equal to RT over R3 times I total. Now, what numbers I'm going to be putting in here? What do I use for RT? Do I use 50 ohms for RT?
12.
I have to use the 12. I have to use what these two guys in parallel simplify to become. The RT we use is not RT for the whole circuit, but it's RT only for this bank of two resistors, which worked out to be 12 ohms that we calculated earlier. So that we're going to use REQ1. So in this case, it will be REQ1 over R2. This will be REQ1 over R3 times I total. And mathematically, that works out to be a 12 over 20. This works out to be 12 over 30. And here we're going to multiply by, to make numbers simple, I'm just going to multiply by 0.5. I can key in 500 milli, but at this point, I'm going to try to keep things simple. Isn't 500 milliamps the same as 0.5? And isn't 0.5 a lot easier to key into my calculator? So right now, everybody, take 12 divided by 20 times 0.5. 12 divided by 20 times 0.5. And what do you get, Pauline?
For IR2, I got 300 milliamps.
Cool. 300 milliamps. And now we're going to take the 12, divide by 30 times 0.5. And Andrew, what do you get here? Avery, going to give us an answer?
Milliamps? 200 milliamps?
So worked out, you're correct, 200 milliamps. 200 milliamps. So we calculate 300 milliamps, we calculate 200 milliamps. Now we have the information 300 milliamps and 200 milliamps. Bingo. So do I have proportional distribution? Which branch has more ohms? R3 has more ohms. It happens to have 200 milliamps flowing up through R3. Which one has less ohms? 20 ohms, the R2 branch. It happens to have more current, 300 milliamps flowing there. Do these two combine to have the 500 milliamps flowing through R1? Yes, they do. So all the hard work was done by calculating, simplifying by redraw 3 resistors to 2 resistors down to a total, calculate a total current, then do current analysis. So the bulk of the work was done using current analysis. So for the bulk of the work, you're doing current analysis, so therefore we're going to be using current divider formula. And once we find the currents, now calculating voltages is pretty straightforward, yes? Because it's just simply according to Ohm's law, V is equal to I times the ohms. Do I have I times the ohms? Do I have I times ohms, I times ohms? So what does this all calculate to be? Now keep in mind, so is you could do this very simply. This isn't 500 milliamps 0.5. What's 0.5 times 38?
19.
So I have 19 volts. This is 300 milliamps, which is the same as 0.3. What is 0.3 times 20?
6 volts.
That's 6 volts. This is 200 milliamps. What is 0.2 times
6 volts.
30? 6 volts. Well, that's very interesting. Does 19 plus 6 plus 6 give me 25? Could that be wrong?
No, it's right because you only do 19 plus 6 once because it's parallel.
Precisely. You nailed it right on the head, Andrew. Best answer yet. We only add the 6 volts one time because 6 volts is in parallel. 6 volts here, 6 volts here. So we actually have right over here 19 volts and we have 6 volts here. So we only add the 19 plus the 6 volts one time to equal 25 volts. Is everybody okay with the VIR chart? Once we have the VIR chart, now are the numbers easy to plug in? Yeah. So let's go back, take this information, and let's go back to the share screen and pop this information in. Back to share, back to here, and let's pop this information in. Cool. So my RT we calculated was 50 ohms, yes? 50 ohms. The IT calculated to be 500 milliamps. Fill that guy in. The IR1 calculated to be 500 milliamps. The VR1, according to our chart, calculated to be 19V. VR2 calculated to be 6V. And VR3 also calculated to be 6V. What was my IR2? According to my chart, IR2 worked out to be
300 milliamps.
300 milliamps. Perfect. And that completes the questions for that particular exercise.
No, you got
So-
45. 45 is 200 milliamps.
There we are. 45 right down here is correct. 200 milliamps. Perfect. There we are. Thank you. So as we look at this exercise, in the absence of a VIR chart analysis, looking at all these blanks that have to be filled in, it's like, oh my gosh, where do I start? And it doesn't present any logical format by which you can deduce these numbers very quickly. So what will never ever fail you is if we go to our old friend VIR chart, draw the original circuit, simplified by redrawing from 3 resistors to 2, determine what's equivalent, take the 2 resistances, bring it down to 1, find a total, find total current, start filling in your chart, use current analysis, current divider formula, figure out your currents, and then the voltage is just Ohm's law. So does that give everybody a better understanding how to approach this?
Yes, it
suggestion,
does.
Colleen.
Thank you.
So you
Yes,
can
it
thank
does.
Colleen.
It helps out
She came
big
up with a
time.
good suggestion. That's great. All right, cool. Now let's go back to our diagram here, our share. Okay, now let's take a look at this guy. Cool. As we take a look at this guy, how would we approach solving these quantities given this scale information here? I have some scale information here. How would I go about solving this?
You look at the information on the top, and then you have to go to the chart and count the boxes over, right?
Cool. Let's go ahead and do that. So I'm going to draw a line through this as much as I can through the peaky peak of it all. Say right about there is where it peaks. So if I draw that line through there as I have, and I go to count how many divisions from the 0 line up to the top. How many divisions do I have from here to the peak?
I did
2.0.
2.5.
Okay, 2.5 is a good number. I'll go with 2.5 also. So if you have 2.5 divisions, what do you do with that 2.5 divisions? Mathematically.
You gotta times that by 15, right?
15 what?
Millivolts.
Yeah, don't forget the milli. So 2.5 times 15 milli. And so that works out to be
37.5.
that's an incomplete answer.
Oh, millivolts.
Almost complete.
Oh, VP.
There you go. Yeah, you got to deliver it all in one
All
fell
right.
swoop, not in chunks. Okay. So let's go ahead. Let me see if I can do it this way. And can I insert a text box on top of a drawing? I don't know. Yeah, let's try this and see. Nah, it won't let me do it on top of a drawing. So let me just undo. Yeah, I won't be able to type the numbers in for us on this because this is not a word. This is an image. So let me just go underneath here and let's just go ahead and type in. So we end up with, Andrew gets 37.5 milli peak. Milli V peak. That takes care of the first answer. Good. And peak to peak is just simply double that, yes? So when you double that, what's my peak to peak?
75 millivolts peak to peak.
I love it. That's how we will state it. 75 millivolts peak to peak. Bam, right there. Now, the next one is calculating RMS. So the RMS, I would use the square root of 0.5 instead of the 0.707 in this case. So what am I going to calculate? How am I going to calculate my RMS?
VRMS is equal to 37.5 millivolts peak times the square root of 5.
Times the square root of 0.5, precisely.
0.5, correct. So
And
which
when
is
you
the
do
answer,
so, you end up with what value, Pauline?
26.52 millivolts RMS.
26.52 milli VRMS would be correct. Cool. Now we want volts average. So Christian, how do I calculate volts average? So I take the V peak and I multiply by 2, divide by pi, and I end up with 23.87 milli V average. Boom. Next one is more interesting. Was there any questions on how to calculate the V average? Is there any calculator issues I can discuss with any of you?
No, I'm good.
Period. How do I determine period? General question to everybody.
I got 1.2, but I don't think that's right.
Well, how is the question? How do I determine period? What is the method?
You gotta find the from one point of the wave to where it starts to repeat itself, and then figure out how many divisions there are in between them, and then multiply it by whatever number we're given for time divisions, which in this case is 300 microseconds.
Okay, so the time per division, T per division up here in the upper corner is 300 microseconds for each division. If you look at the picture shows, if you take the positive peak to the positive peak, could we do that? Let's say we start at the positive peak, follow its rotation down to negative peak, back up to the positive peak. Between here, where my cursor is, and here where my cursor is that the distance of the cycle? Sure. How many squares do I have there?
4.
4 squares, 4 divisions. Could I go from the negative peak to the negative peak? How many squares do I have between the negative peak to the negative peak? 4 squares. If I start at 0 right over here, and I go up to the positive peak, down to 0, go to the negative peak, back to 0. So between here, the dead center of my O-scope, and here, the beginning of the form, do I have 4 divisions? Yes, I can take that count anywhere for one cycle. But do we agree that I have 4 divisions between the beginning of the cycle and the end of the cycle? And what I do is I take the 4 divisions and I multiply by 300 microseconds. And when I go to do so, what do I get? So Andrew, you shouted out an answer.
I said 1.2.
You forgot micro.
Microseconds.
No, you forgot to enter the microseconds in there.
Oh, okay.
4 times 300 microseconds. should give you 1200 microseconds, but your calculator should show you 1.2 milliseconds. So your 1.2 is correct, but you need to follow it up with a metric, and you need to follow it up with a quantity. It's not 1.2 millivolts and milliamps, it's 1.2 milliseconds.
Milliseconds.
Okay. So once you have that, so it's 4 times 300 micro, 1200 micro, 1.2 microseconds. So the question, how do I determine frequency? Question goes to Gabe. How do I determine frequency? What's the relationship? What's the relationship between frequency and period? Pauline.
They're reciprocal, so therefore 1.2, and then reciprocal, the answer should be 8.33 kilohertz or hertz. I know I got the wrong period. Sorry.
Type in 1.2 milli and then hit your reciprocal key.
One,
It equals, what do you get?
I get 833 hertz.
Millihertz.
Nope.
No.
So it's 1.2 micro.
No, 1.2 milli.
Sorry. And then, yeah, so it's 833.33 hertz.
Mm-hmm.
Am I getting it wrong?
Perfect. 833.33 hertz. And there you are. So an alternative would be this. Let's go ahead, stop the share for a moment and go to here and clear the calculator from the top. You would take your 2.5 divisions and you multiply this by 15 millivolts per division. And that's how you key in your milli. So 2.5 times 15 exponent -3 is your milli. And that's how we end up with 37.5 exponent -3, which you have to write down as 37.5 millivolts peak. You got to keep your engineering prefixes. Then when you double that times 2, that's your volts peak to peak. So it's 75 millivolts peak to peak. When we go to calculate the RMS, it's the peak value, and we're going to multiply this by the square root of 0.5. So if I take the peak value of 37.5 milli times the square root of 0.5, I will end up with my 26.52 exponent -3. So that's how I get my 26.52 milli VRMS. When I go to calculate my V average, I'm going to pull my V peak back, and I'm going to multiply this by 2 and divide by pi. So my 37.5 milli V peak times 2, divide by pi, and that's what gives me my 23.87 with the exponent -3, my 23.87 milli V or milli V average. The period was calculated as 4 divisions times 300 micro. And micro is exponent -6. So 4 times 300 exponent -6, 300 micro. So 4 times 300 is going to give you 1200 micro. But the calculator, because it's set in engineering mode, to show me 1200 micro. 1200 micro is not proper engineering notation. It fixes it for me, gives me proper engineering notation of 1.2 milliseconds. Once I have the milliseconds, as Pauline said, period and frequency are reciprocals of each other. All I have to do is hit my reciprocal key, reciprocate that previous answer here, and I calculate 833.33 hertz. Is everybody okay with the calculations and how it gave us the answers that I have highlighted in yellow on our share screen? Everybody okay with that? Any questions on this exercise? Okay, number 47. 85 volts RMS sine wave, voltage attached to a light bulb, AC source is disconnected. What would be the DC voltage that would be needed to produce the same amount of brightness? Christian, what do you think?
Okay, hold on. Let me see. An 85 volts RMS.
It's a concept question. It's not a calculation question.
The average, the peak is equal to the DC voltage, no? No, wait a minute. An 85 volts. Yeah, it'll be the peak of whatever 85 volts was. That'll equal the DC voltage.
That's a good thought. That's a good thought. I like that thought. Does anybody else have a thought?
I had to admit, I did not know the answer to this one, so I left it blank. I was
Yeah,
kind of hoping it.
I'm the same with Pauline. I skipped this one. I didn't know.
Okay, so here's the question. What
I
was
did the same
significant?
thing.
Yeah, what is significant about RMS? And the 120 volts that we have coming out of our wall sockets is 120 volts RMS. So it is an RMS value that PG gives us. The significance about RMS is it is the version. Remember, there's several versions of AC. We saw in the answer previously up above, there's a peak version of AC, there's a peak-to-peak version of AC, there's an RMS version of AC, and there's an average version of AC. There's 4 different versions of AC. What the heck are we going to do with that? What is significant to us? What does PG&E tell us? PG&E gives us the RMS version. And so when you're faced with this, what is significant about RMS is it is the value of these 4 different versions. It is the version of AC voltage that is equivalent to the amount of work that the DC voltage will do. So in order for the light bulb to produce the same amount of brightness using a DC voltage, given this amount of 85 RMS, it would be
85 volts.
85 volts DC. That's what's significant about RMS. RMS and DC numbers will do the same amount of work. Okay? If this was given to you in peak, then you'd have to calculate what the RMS would be, and then that would be the DC. So if, for example, this were rephrased, if let's say 95 V peak AC was lighting the bulb, blank equals the DC voltage equivalent to light same level. Okay, so if this was the question that was posed to you, how would you play with this? You would have to take that V peak and convert it to RMS. Whatever form of AC you're given, you got to get it into RMS. So calculate based on 95 volt peak. Give me an RMS value. What do? You take the 95, you multiply by the square root of 0.5. Everybody do that right now. And your number, Gabriel, 95 times square root of 0.5. What do you calculate?
I got 67.1 volts. Or
Equals 67 point what?
67.1.
Remember, all our answers since the beginning of the semester are 2 digits after the decimal point, properly rounded off. So what should this be?
2.
2 digits after the decimal point, my friend. Everybody, go ahead.
So
67 point.
67.17.
What's my third digit?
18, sorry.
There you go. You got to look at that third digit. You better end up with a 18. VRMS. So VDC equivalent equals 67.18 VDC. Boom. That's how you would do that. So did this added example help clarify some things for you regarding RMS versus DC, everybody?
Yes.
Okay. Next, 3 capacitors. Okay, could you mute your microphones, please? Thank you. So 315 microfarad capacitors connected in series. Calculate the CT. How would we do that? Is there a shortcut?
Yes. You divide 15 by 3.
Yep, 15 by 3 would very quickly give you
5.
5 what?
5 microfarads.
5 microfarads. It would not just give you 5. We don't respond to just numbers. You have to give the proper engineering and electrical quantity. So 5 microfarads, because you would use reciprocal method, or you could use a shortcut. And the shortcut is, if you're going to use reciprocal and they're identical values, simply take 15 and divide by, in this case, 3. Gives you 5 microfarads. If these 3 were in parallel, how would you calculate the total?
You would add?
Okay, so what would we have?
C1 plus C3 plus C3.
So what's the total work out to be?
45 farads.
45 what? What's my engineering unit?
Picofarad.
No, that's a U. A U is a micro. You have the magic card in front of you, use it. Okay. Okay, I see Mr. Lau joined us. Glad you could join us. Very important. Okay, so Mr. Lau, since we have a final tomorrow, could we check and make sure that you have some sort of a camera device that I can observe you on the other side? Mr. Lau, unmute your microphone. Mr. Lau is having some technical challenges now. He will get back to us. All right. So an LED requires 15 milliamps, 1.5 volt source connected, and a series limiting resistor is shown. If the voltage is set to 6, what resistance would you specify for the current limiting resistor? How would you approach this exercise? Question goes to Christian.
An LED that requires 15 milliamps. Hold on, 'cause I gotta figure out.
Yeah, give it some
Word
thought.
problems
Give it
always
some
get me
thought.
like confused. Even if I get them right, it takes me a while to like figure out exactly what it's asking.
Mm-hmm.
An LED requires 15 milliamps.
I read it like 5 times, bro. No worries.
Yeah, it's kind of like the multiple choice things. It's just they all look the same.
Well, here's what I would submit for you all to think about. You're given a bunch of facts. Why don't you lay out the facts?
Oh. 15 milliamps at 1.4 volts.
So your I is equal to 15 milliamps.
And
And what else?
the voltage is 1.4.
Well, how is that different from the 6?
Oh, it's let me see, 6 divided by 1.4.
No. How is it different? You got 2 different voltages there. How would you label them? It says power supply is set to 6 volts.
Then it'd be 6 volts.
What is 6 volts?
The power supply.
Yeah, but how would you label that in terms of your facts?
Oh, I don't know. I'm confused.
How about VS or
Oh.
VT? Okay, isn't the voltage source and voltage total, isn't that going to be your 6 volts?
Yeah,
Would that be a good fact to have?
that's a good start.
Well, that's where I would start. Okay, so VT is equal to VS, which is equal to 6 volts. And then you got 1.5 milliamps flowing in the circuit. So how would you label the 1.4 volts? What's equal to the 1.4 volts?
The LED voltage or what?
Yeah, VFD is equal to 1.4 volts because that's what it requires. So you have another fact. Okay. So how does that help us out? So you got a VLED. I'm going to make a subscript here. Watch this. Home and subscript. Boom. So now I got VLED. So I got a voltage total, same as voltage source is 6 volts, 15 milliamps is my current, and I have a voltage on this guy here. And it says, what resistance would you specify for the current limiting resistor? Well, in this circuit, how many things do you have?
I got
How many devices do you have?
got a resistor,
Got a resistor?
an LED, and a power supply.
Good deal. So could we take those facts? Could we take those facts and do something like this? Take the facts, stop the share, and let's just go ahead and look at another piece of paper. And so could we do this?
Would it be 400 ohms?
Yeah, I want to show everybody a method of how to determine this and not guess. So do we have a resistor? And do we also have an LED? And do we have total? So instead of a resistor 1 and 2, you have a resistor 1 and you have an LED. What facts are you given? You're given that you have 6 volts total. You're given that the voltage across the LED is 1.4 volts. And you're given that the current is 15 milliamps. So you have 15 milliamps. And is this a series circuit? If you go to draw this out, here's your voltage source, okay? And here's your LED. I'm going to draw the LED correctly like so. So here's your LED. Here's your current limiting resistor. So here's your R1 and here's your LED. And your S, and you have the 6 volts. Nerd. Where's my correcto thing? It's around. Here we go. 6 volts. And you're given that across this guy, this is going to drop 1.4 volts. volts. And in this circuit, you have positive, negative. You happen to have 15 milliamps flowing through here. So from the drawing that you have in your practice sheet, is this schematic an equivalent to what you see on your paper? Do I have a power supply? Is the power supply hooked up to an LED? Is it hooked up to a resistor? Are they hooked up in series? The current have to go through one before it goes through the other. The answer is yes, and they are in series. Are the facts given that I have 6 volts on the total? Are the facts given that I have 15 milliamps flowing in the series circuit? Are the facts given that I have 1.4 volts across here? What do we know about voltage total and the voltage drops that have to happen along the way? Is there a way I can determine what the voltage on this guy is going to be? What is my voltage going to be on this resistor? Doesn't this voltage plus this voltage have to add up to 6?
Yeah.
They have to, because this is the total. So you're given 1, you're given the total. Can you find the missing voltage? Yeah. Just go ahead and take 6 minus 1.4. What's 6 minus 1.4?
4.6 volts.
4.6 volts right there. That wasn't so hard, yeah? So far, so good?
Yep.
Now, this is a series circuit. What is the same in all parts of a series circuit?
Current is the same.
Current. Wow, if current's the same, if you know one current, you're given the current, can you fill in the current column? Yep, because they're in series. Do I have enough information in order to use my friend Ohm's law, V, I, R? Do I have enough information to calculate the R? Sure do. What R do I want? I want the resistance of the resistor. I want this guy right here. Can I calculate this missing current right here? According to Ohm's law? Would you do that, please?
By 15 milliamps, it'll be
There you go.
3.67 ohms.
Hallelujah. So that works out to be, now, are you going to give that to me in proper engineering notation?
At
4.6 divided by 15 milli, yes?
I got 306.67 ohms.
Uh-huh. Anybody else agree with Christian?
Yeah, I got the same.
I agree.
So it worked out to be? Christian, call that number out again.
306.67 ohms.
306.67 omegas. And that's what my calculator calculated as well. Everybody okay with that? We don't need to calculate this. We don't need to calculate this. That wasn't asked. But could we take any written scenario? Yeah, I read it 5 times myself if I didn't take the time to draw the picture out. But I would read it and try to determine the facts. What are the facts with respect to a VIR chart? What are the facts with respect to a circuit? What's the circuit in the picture? What's that drawing in the picture look like as a schematic? And it should look like this: voltage source, LED, resistor. There's only one current path. They're not in parallel. Therefore, the current must be the same. If I'm given 15 milliamps must fill in the entire column. If I've given the total voltage and I'm given that the LED drops 1.4, then the difference must be 4.6 across the resistor, because we know the 4.6 plus the 1.4 have to add up to be the 6 volts given. Once you have the voltage of the resistor and the current going through it, basic Ohm's law, 4.6 divided by 15 milliamps, bam, there's your resistance. Are we okay with how that's done? Let's go ahead and do this guy. Back to here. So on here, this calculated to be 306.67 ohms. Oops, ohms was already there. Cool. Okay. So we use these facts, and we also use the VIR chart. Next, you need to calculate one time constant, calculate the time for one charge. If the cap is coded this, calculate the capacitance, calculate one time constant using a different resistor, calculate the time required for the cap to charge up to 15 volts. Okay, a lot of good questions on this particular sheet. So you have an RC circuit, and what do you remember about calculating time constants? What is a time constant? What is the circuit about? You have a DC volts, you have a resistor that limits current, you have a capacitor. What's the job of the capacitor? The job of the capacitor is to store charge. In order for it to store charge, it has to have a voltage source to charge up to. This capacitor will ultimately charge up to the full 15 volts. When the switch is closed, there will be current flowing through the capacitor, charging it, and ultimately, when enough time goes by, the capacitor will reach the full 15 volt charge, and at that time, the current will stop. We've seen this before in previous analysis and drawings. So how do I calculate time constant? Simply R times C, which is equal to, what's my R in this case? 10 kilo ohms. Oops. Get my omega back. Copy. So 10 kilo ohms. And I'm going to multiply that by 100 microfarads. 100 microfarads. Okay, I got it typed out for you. You got to do the math. Ten kilo times 100 micro. You got to know what power of 10 micro is. So this calculates to be what time for one time constant. Question goes to Kyle.
I got 1 second.
How many people agree?
I agree.
1 second. Good job. So, given the 15 volt source, how much time will be required for the cap to charge up to the full 15 volts? Question goes to Andrew.
I'm not too sure on this one.
Well, time constants.
5 seconds.
It would take 5 time constants to reach full charge, 5 time constants to reach full discharge. So what's 5 times 1 second would be 5 seconds.
5 seconds.
If the cap was coded as a 473, now recalculate the capacitance. Or calculate the capacitance based on 473. So how do we do that? So that would be 4, 7, how many zeros?
3
3 zeros. And what do I end up with? What unit do I have here?
nanofarads.
No. When the first part of the conversion is you enter the first digit, the second digit, number of zeros. What happens at the end of this line?
Times 10 to the 10 negative 12.
Yes, which is picofarads, which is 10 negative 12. And then that converts to be what number of nanofarads?
470 nanofarads or 4.7.
Neither of those answers are right. It's not 470, it's not 4.7. Just move the decimal place 3 places. Or enter this in your calculator. Your calculator will give you the correct answer.
Nano.
So Gabriel, what's your calculator show you?
I keep getting the 470 nanofarads.
You're not going to get 470 nanofarads. Okay, let me show you what you need to see on your calculator. Everybody sees the calculator? Okay, so I'm going to type in the 4 and the 7, yes? So far I got a 4 and a 7. I'm going to type in 3 zeros, 1, 2, 3, and then pico. What power of 10 is pico? Pico is exponent negative 12. That's what I got to key in. So it's 47000 pico, which is 10 exponent negative 12. The moment I hit enter, the calculator in the engineering mode automatically shuffles around, gives me the correct 47 nano. It's not 470. You're not going to get 470 or 4.7, which is what I was saying. So if your calculator is set up properly in engineering mode, you can only get 47 nano.
It was set up right. I wasn't looking at my calculator. I thought I seen 4.7, but it is 47.
Mm-hmm. So you got to be careful tomorrow on the final exam. You got to read your calculator carefully. There is no decimal point between the 4 and the 7. Don't misread it. Don't rush. It says what it's supposed to say. And so type in 4, 7. Okay, don't let your calculator do all the work and all of a sudden you interpret it incorrectly. That would be not good. Okay. All right, so now recalculate one time constant with R being equal to 10 k ohm. So 10 k ohm is what we originally had, but we have a new capacitance now. So this would still be R times C, which is equal to, let's go ahead back to my share screen. So it's equal to R times C. And so in this case, it's still equal to 10 K ohm, and multiply by, in this case, 47 microfarads equals. So with this new capacitor in here with the same resistor, what do we all calculate? So you take your 10,000 and multiply by 47 nanofarads. Sorry, 47 nanofarads. So 47 exponent negative 9. All right, so the calculation works out to be what amount of time? Question goes to Pauline.
I get 470 microseconds.
So 470 microseconds is correct. And then now calculate the new time for this to charge up to 5 time constants. So Andrew, back to you. If one time constant is calculated and agreed at 470 microseconds, how long will it take to calculate to 5 time constants for the full charge? Multiply the previous value times 5, the 470 microseconds times 5.
235.
Look at your decimal points.
2.35.
2.35 what? What power 10 do you see there?
3
Okay, so call it out. What
milliamps.
engineering is power
I mean
3?
milliseconds. Sorry, milliseconds.
Okay, because I heard all kinds of things other than the right answer. But when you slow down a little bit, read what your calculator correctly calculated for you, because you entered all the numbers right. Don't mess up reading your calculator. Okay? So it's 2.35 milliseconds. Is everybody okay with that? So far, so good? Okay. Control S. Let's go ahead and save that. Cool. Next. All right. Which knob? Oh, we're talking about knobs. So which knob are you going to adjust for seeing fewer cycles on the screen? Fewer cycles on the screen. Kyle, what do you think?
The one that adjusts the time.
Okay. So we will call, and it's labeled as time base. Okay. That will show you fewer cycles on the display. Cool. And which knob will show you, allow you to view taller cycles on the screen? Go ahead, Kyle. Finish this up.
The vertical.
Vertical. Done. Bravo. Okay, last page, my friends. We're getting there. So far, so good. So why might electrolytic capacitors cause a shock hazard? Question goes to Pauline.
Because the electrolytic capacitor is made up of two thin layers of metal sheet, and we know capacitors having to store some energy even without any power source. So that's why it can cause a shock hazard.
There you go. I agree with you. We could sum it up this way. They can store lots of charge. Boom, boom. So watch out for those. Okay. This is really interesting. Huh. What do we have here and how do we determine my voltage total and my I total? Well, this is kind of challenging since I didn't give you a value of R. Okay.
Yeah. So I got this one, and
let's say R is equal to 10 ohms. Let's make R
okay,
10
good.
ohms. If R equals 10 omegas, well, comma, there you go. So what's my voltage total? And what's my current total now that I give you an ohms? What do you think, Pauline?
Well, looking at the diagram, I see that they're opposing, which means I've got to deduct 12 from 10 volts. I mean, I'm sorry, yes, 10 from 12 volts. So I get 2 volts.
2V.
And now that you've given us the R, IT should just be 2 volts divided by 10 ohms. Which is 200 milliamps.
Bingo, you got it. Done. Cool. All right, now on to something more interesting. Gabriel, why don't you try number 60? Tell us what's going on with this. Because ohms are given in this one.
Looks like they're telling us what way or not telling us, but they're marking already where's the positive and negative on each resistor of what way it's traveling. So I would say BT would be
So we recognize we have two voltage sources on here. Are these voltage sources series aiding or are they series opposing? Remember the difference between the terminology. What is series aiding? What is series opposing?
They're opposing. They're going against each other.
Yeah, they're going against each other. So you have series opposing. Series aiding would be if they're helping each other. Here they're opposing each other because they're moving current in different directions. So if they have current moving in different directions, like the previous exercise that Pauline played with, how do I find my voltage total given these numbers that are on the screen? What do I do mathematically?
Subtract
Okay, so do the subtraction. What do you get?
24 volts.
24 volts. Everybody in agreement with 24 volts? Good deal. We have 24 volts. So how do I calculate my RT? Continue. You're on a roll.
They're in series, so just add them.
Add them. So how many ohms do I have total here?
12 ohms.
So you have 12 ohms. So 12 omegas. Done. So how do I calculate my RT?
2 amps.
2 amps. 2 amps. There. Didn't even need to pick up the calculator. You did that in your head, I bet.
Yeah.
Yeah, good job. Any questions on that, my friends? Okay, on to our phase shift exercise. So we have the phase shift exercise. You're given the formulas. You're given the formulas in view. You have your x sub c is equal to 1 over 2 pi fc. You're given your z. Z stands for impedance, which is total ohms. So that is a Pythagorean Theorem formula. And you have to calculate the angle of theta, which is inverse tangent of your reactance over your ohms. So you happen to have some information you can work with on your schematic. On the schematic, do you see the resistance in the circuit? How many ohms do I have here? Mr. Lau, are you with us, Mr. Lau? Are you back with us, sir?
What?
I'm glad you're back with us. Thank you. So for the final exam tomorrow, you have to have some sort of a camera that I can see you.
Like you teachers that have
My
kids.
camera? I know I
Yeah.
have it, but I only have the phone camera.
Kids may not even
Okay,
know
you only have a phone camera. All right, so you're watching our Zoom. So how are you going to take the final exam tomorrow? Do you have a computer that you can use?
Computer? Yeah,
Mr.
right now
Lau,
I'm using.
do you have a camera, excuse me, do you have a computer you can use for the examination?
No.
Is that a yes or no? I didn't hear that really.
Yeah.
You have a computer. Okay. Is
Yeah,
the
I have a
computer
computer.
is the computer a desktop computer or is it a laptop computer?
Desktop.
Desktop computer. Okay. And so with a desktop computer, then you also have your cell phone. So with your cell phone, can you put yourself, do you have a camera in your cell phone?
Yeah.
Okay, that's great. So you can see the exam and then I can see you also. So you're looking right now, are you looking at this information on the computer? Can you see the screen that I'm talking about on your computer? Can you see the phase shift waveform on your computer
I
screen?
see it, but cell phone,
Good.
I didn't. It can't.
Yeah, we don't want you to do your work on the cell phone. The only thing I want you to do on the cell phone is to show me a picture of you. Can you show me a picture of you on your cell phone? Do you have a video function on your cell phone?
Let me do everything. 9.
Okay, Mr. Lau, you and I will hang tight after the session because we need to discuss how you're going to set up being able to take the examination tomorrow, okay?
Okay.
So at the end of this session, just stay with me afterwards. Yeah, I see your cell phone working and I see your eyeballs, which is a good start, but you and I will talk about this afterwards. So that's a good start. All right, but you can see the computer screen. So on the computer screen, can you see the value of R? How much ohms do I have for the R?
2K.
2K ohms, good. And can you see the value I have for a capacitor, C1?
Number 373.
For 373, very good. Okay, I'm glad that you can see all that. And how about the frequency? Can you see the frequency okay?
Yeah, I say 4.45 K on
Kilohertz.
gigahertz.
Yeah, kilohertz. Okay, so 4.45 kilohertz. All right, so based on that, we have some questions to answer down below. So these questions that we're going to need to answer are here. Let me eliminate the pages. So we have to answer, what is my volts peak coming into the circuit? What is my capacitance value? What is my reactance? So let's take this one by one. Let's go ahead and do V in peak. Do you see my voltage source? My voltage source is what listed here is how many volts?
20 volt peak to peak.
Yeah, 20 volts peak to peak. So if it's 20 volts from here all the way down to here, what is my volt peak? What is from the 0 line to here? What is half of that?
So top.
Yeah, what's half 20 volt peak to peak?
I don't know.
Well, half of 20 would be 10. So it would be 10 volts peak to 10 volt peak. Okay, so that's how you would answer the first one. All right, now the next thing we are asked to do is to determine the value of capacitance. So everybody, you have a 373. So what you need to do is you need to code your 373. Take your 373 and determine what the capacitance of that works out to be. So let me go ahead and stop the share. And here, let me go back to my camera. Okay, so a 373 cap. We interpret that how? As a 3 and a 7 followed by how many zeros, my friends? Everybody? 3 zeros. And what do I end this line with? Gabriel.
P.
P what? P what?
PF.
Farad. So capital F stands for farad. What do I key into my calculator in order to convert this to proper engineering notation? So I will key in 37000 exponent negative what? Pico is negative 12. Then I will hit equals. And so when I do that on my calculator, as you will do on your calculators, 37 followed by 3 zeros, exponent negative 12. Let me just clear this so it's a clearer display. So 37, 3 zeros, exponent negative 12. So do you all convert 37 nanofarads?
Yeah.
37 nanofarads. So I will put that in for my value of capacitance. My value of capacitance will be 37 nanofarads. And then you are asked for, the next value you are asked for is X sub C. So this is equal to C. So x sub c is equal to 1 over 2 pi fc. So in my calculator, this would be 1 over 2 times pi times my frequency, which is 4.45 kilo, and then multiplied by my 37 nanofarads. So how would I do that into my calculator? A couple of ways. Some people might do this 1 and then divide by, open parentheses, 2 times pi times 4.45 exponent 3 times 37 exponent change sign negative 9, nanos of 9, and then close parentheses and then hit equals. If you do this keystroke sequence, you should be successful. 1 divided by open parentheses 2 times pi times 4.45 second exponent kilo, and then times 37 second exponent negative 9 close parentheses. And what value of x sub c do you calculate as a result of this? X sub c works out to be what value? Question goes to Andrew. Do you have a value?
Nine.
1 second.
I'm doing it right now. I'm closing it. So it would be 966.62.
What units?
Uh,
X sub c is reactance measured in units of
you got me.
ohms.
Ohms.
62.63.
63 because of the 5 rounds up.
Yes, there you go. And this would be ohms. Everybody okay with x sub c? So x sub c works out to be 966.63 ohms. So the next thing you're asked to calculate is your Z, and Z is called impedance. And what is impedance? Impedance is equal to total ohms in this circuit, total ohms, which is equal to your R ohms as well as your X sub C. So you have two different kinds of ohms here. You can't add them up with each other because they're not in phase with each other. So what it is that we need to do is use the impedance formula, and that was given as square root of R squared plus X sub C squared. So that's going to be equal to, in this case, 2K squared plus 966.63 squared. And you all square root that, I'll give you some value. So as close as you can on your calculators, let's do this. Second square root. I'm going to grab this number, square it, add it to 1,000, square it, and I will have a result. Gabriel, do you have a number yet? Pauline?
I have a total of 2.22 kilo ohms.
That would be correct. And so 2.22 kilo ohms. So mathematically, my friends, this is what you're doing. What you're doing is this is out of phase waveforms. So we happen to have an R phasor that's traveling along here, and that's 2 kilo ohms. We happen to have a X sub C phasor traveling down here. Here's my X sub C, and the X sub C is equal to 966.63 ohms. What it is that we're trying to do is we're trying to calculate how these two guys add. Now, they don't add straight up with each other because they're out of phase with each other. One is 90 degrees out of phase with the other. So from the beginning to the end, by adding these, we will have a resultant. And the resultant on a right triangle, because they're 90 degrees apart, that is Z. Z is your impedance. And Z works out to be 2.22 k ohms based on this guy squared plus this guy squared square root, boom, gives you the hypotenuse of a right triangle. And according to Pythagoras, 2.22 k ohms. Once you have 2.22 k ohms, do we have enough information to calculate our current? Because keep in mind, all of this is for a wonderful C circuit with a 10 volt peak. We have a capacitor, and we have a resistor, 2 k ohms. This guy goes to ground, this guy goes to ground. This is my V out, and this is my C. And the C is a number 373 cap. So what I'm calculating now will be my I total. So I total is going to be equal to V peak over, so my I total in peak is going to be V peak divided by my total ohms of 2.22 kilo ohms. Now, if you're 1/100th of a decimal of a digit away from my 2.22, you're still in good graces. So take 10 and divide by these ohms. And what do you calculate for a current? So take 10 volt peak, divide by, write too fast. Volt peak, and divide by 2.22 k ohms. Kyle, you have a number for me yet? Gabriel? I'm only asking you to divide 10, divide by 2.22 k ohms.
I got here. I got 4.5 milliseconds.
Current,
Oh, sorry, yeah, milliamps.
4.5 milliamps is your I total, 4.5 milliamps peak. Because if we start off with 10 volt peak, then we'll have a milliamp peak. So I total peak works out to be 4.5 milliamp peak. Cool. Now, based on that, do we have enough information to calculate the voltage for the resistor? How much of the 10 volt peak is going to be on the resistor? How much of the 10 volt peak is going to be on the capacitor? Do I have enough information?
Yeah.
Sure do, because I'm going to save a little space over here, help you all out. We could do this. We have two components, and we're interested in VIRs. So can we do a V on omega chart? And can one of these be R, which is clearly going to be 2 k ohms? Can one of these be the X sub C, which we calculated as 966.63 ohms? And we have a total, and the total worked out to be 2.2 k ohms. And we determined a current here of 4.5 milliamps peak. Is this not a series circuit? If this is a series circuit and I have 4.5 milliamps peak, do I know the current that flows through the capacitor as well as these arrows go both ways? Why do these arrows go both ways? Because this is an AC signal. Do I know the current through the resistor? Yes, 4.5 milliamp peak. Do I know the current through the capacitor? Yes, 4.5 milliamp peak. Is this chart easy to construct based on two components in a VI ohm? I'm not going to call this R because R pertains to resistors only. I have a capacitor in here. So the ohms for a capacitor is X sub C. That's capacitive reactance. So I'm going to label this VI ohm. Same idea. 2 K ohms, 966.67, total of 2.2 K, calculated 4.5 milliamps. Oh, by the way, I do have a 10 volt peak as my source. Do I have enough information now to use my friend, our friend, Ohm's law, VIO, in order to calculate these voltages? Sure. I know the current that goes through the circuit. All I have to do is take I times ohms, yes, in order to calculate V. Doesn't that Ohm's law chart show me this? If I want V, isn't V equal to I times ohms? So go ahead and do the math. 4.5 milli times 2K, the milli and the K cancel each other. So mathematically, it's simply 4.5 times 2. How many volts does this work out to be? 4.5 times 2. You don't need a calculator.
9
9 what?
volts.
Volts what? Peak.
Peak.
Peak current, you're going to have peak voltage. So far, so good? Okay. So the only other value of voltage you need to calculate is this guy here. You got to multiply this times this in order to equal to what we have here. So let's go ahead and do that. So you take your 4.5 milli and you multiply this by your 966.63 ohms, and you'll calculate a voltage. What do you calculate?
I got a 4.34 volt peak.
Look at that third digit.
4.35.
Okay. So 4.35 volts peak. Is that pretty straightforward math? Just I times R gives you, I times ohms gives you 4.35 volt peak. Everybody okay with that number? So now you look at this, you scratch your head and you say, well, you know, Co, I'm not so sure. According to, I have across this guy from here to here, 9 volt peak. And across this guy from here to here, I have 4.35 volt peak. And in a series circuit, in a closed loop, in a series circuit, I've been told this voltage plus this voltage in series must add up to the 10 volt source. What's wrong with my math? Does this look like 4.35 plus 9 could possibly add up to 10?
No.
Did we do something wrong?
Not wrong. It's just that they're out of phase, so you can't add them together, right?
Correct, Christian. You can't add them straight up with each other because they're out of phase. They're out of phase, which means we have to do this. So I'm going to draw this out for you. I'm going to have a phasor coming out here. I'm going to clean this up a little bit because I got a little ink on my okay. Got some smudgies here. Okay. So I have a phasor here, and I'm going to call this VR equals 9 volts peak. And then coming down this way, I have a V X sub C, and that's equal to 4.35 volts peak. Guess what I'm going to calculate on this right triangle, this hypotenuse. How am I going to label this hypotenuse? This hypotenuse was Z because this had to do with ohms. How do I label this hypotenuse? I have a VR plus a Vx of C. What should this be labeled as?
It's V total.
V total. And I can't add them straight up because if I try to add them straight up, for sure they're not going to add up to 10. So I have to use our friend Pythagorean Theorem. So my V total is going to use the Pythagorean Theorem formula. So V total is going to be equal to the square root of 9 volts peak squared plus 4.35 volts peak squared. And all of this is underneath the square root symbol. And when you go to do the math, let's see what we end up with. Let's see what we end up with on this. Clear? I'm going to do the square root, open parentheses, take 9, square it, hit plus 4.35, square it, close parentheses. Would you like me to write that out here also? Vt is equal to square root, open parentheses, 9 x squared plus 4.35 x squared, and then close parentheses, and then equals. So there's your complete keystroke sequence. And when you exercise your complete keystroke sequence, enter into your calculator. Before I hit my answer, could you give me what your answer calculates to be? Andrew, do you got a number for us? Kyle, might you have an answer for us?
Not yet.
Yeah, it's a few button pushes, so be patient with yourself. Watch your fingers. Fingers are bigger than the buttons, so make sure you don't end up pushing 2 buttons at the same time. Gabriel, you have a number for us yet?
Yeah, I got 9.996.
Yeah. And if you use, as I did, all the memory in my calculator with all the trailing giblets and keyed it in, and then down with an answer, or even if we didn't, let's go ahead and just take the 9, 4.35. So you end up with 9.996. How would you round that off to the second digit?
Oh, it's going to be 10.
It's going to be 10 volts. And what did we start off with, my friends? 10 volts. Mr. Kirchhoff happy?
Yep.
10 volt peak. Yippee-ki-yay, yes. This part's looking good. This part's looking really, really good. Last thing to calculate is this thing called theta. And thing called theta is an angle. And that is an angle from which this horizontal drops down to the hypotenuse. That is an angle we call theta. We could do it using this triangle, or we can also do it using this triangle over here. Here's the, right. And we're going to do this. I gave you a formula on your worksheet, and that is equal to the inverse tangent of the x value. So here's the x value over the r value, or you can do the inverse tangent of this x value over this r value. Either way, we should end up with the same theta. Let me give you a moment to do those calculations while I fill in some numbers on our answer sheet. And then I'll be calling out for values in a moment. So Andrew, do you have a number for me?
I think I do 48.33.
Could be right. Somebody else agree with 48.33 degrees?
I get 25.79 degrees.
Yeah.
Oh, okay. Who agrees with 20? What did you call out, Pauline?
25.79 degrees.
25.79 degrees. How many people agree with that?
I agree with Pauline. I just rounded it off to 25.80.
Yeah.
Okay. All right, so I'm going to take an x of c value, which I have here earlier. Take this and then now divide by 2000, close parentheses. And yeah, that would round out to be, in this case, 25.80 degrees. So angle theta is equal to the inverse tangent of x sub c over r, which is equal to the inverse tangent of 966.63 over 2k, which works out to be 25.8 degrees. And technically, since this is pointing downwards, it's a negative 25.80 degrees. So that's what we calculate if we happen to use the ohms. Can we go ahead and try that on this side, where my angle theta is equal to my Vx sub c over my Vr, inverse tangent. So inverse tangent of 4.35 over 9. So inverse tangent, open parentheses, 4.35, this value, and divide by 9, close parentheses, and we end up with 25.80. So negative 25.80 degrees. There and there. Everybody okay with how to calculate theta based on this?
I found out what I did wrong. I forgot to put in tangent. I just tried to take the 4.35 and divide it by 9.
Well, it's inverse tangent, actually.
Yeah,
So it's not just tangent, it's inverse tangent.
yeah.
That's the tan negative 1. So this solution here, we can transfer all these numbers back to our answer sheet. So the answer sheet started off with a 10 volt peak, and then we converted that to this code number into 37.5 nanofarads, which allowed us to calculate a reactance of 966.63 ohms, which then allowed us to plug into the formula for impedance, and impedance calculated to be 2.22 kilo ohms, which then allowed us to calculate a current using Ohm's law of 4.5 milliamp peak. And 4.5 milliamp peak in a simple series circuit is the same current throughout. And then that allowed us to calculate each of these voltages based on Ohm's law. And we were able to confirm using Pythagorean Theorem that the 9 volt peak opposed to the 4.35 volt peak gave us a total voltage of 10 volt peak, which worked out beautifully. And then over here, the ohms using Pythagorean Theorem also calculated and verified that we had the ohms of this value. Then we were able to use the inverse tangent formula on this side of inverse tangent of the reactance ohms divided by resistive ohms, gave us negative 25.80 degrees. And then the same over this side, same principle of taking inverse tangent of reactive voltage over resistive voltage, and that gave us negative 25.80 degrees here as well. So 20, negative 25.80 degrees. Cool. Well done,
I have a question.
my friends.
Yeah, I got all of the calculation. However, what was the empirical reasoning behind it being a negative theta again, based on your drawing there? How
Yeah,
do we know that?
yeah, based on the drawing, the x sub c arrow points downwards. If this were an inductive circuit and we calculated encoded value for the inductor and then calculated, instead of capacitive reactance, we calculated x sub L inductive reactance, my x sub L arrow would be pointing up. And the reason why this one points down and this one points up is a whole nother lecture altogether, which you'll see in another semester of electronics. But for now, simply accept x sub c points down, which gives us a negative theta. And if this were a coil instead of a cap, then my x sub L would be pointing up, which would give us a positive theta. And the same would hold true for the voltages. My voltage for an inductor would be pointing up, giving me an angle that goes upwards, giving me a positive degree angle.
Okay, so our previous exercises then should have had a negative theta.
Yes, I didn't bring that up as a point of concern at that time, simply because it begs for more questions to be answered, and that is, well, why theta? Why negative? Well, it's negative because this one comes downward, this one comes downward. Why does this come downward? Because the other one goes upward. Well, why does one come down? Why does one come up? Is a whole nother lecture for another time. So
okay,
for the time being, yeah, our angles technically are supposed to be negative. If you don't put down negative, that's fine. You get the number. I'm very happy. Kirchhoff's happy. Theta's happy. You're happy.
okay.
A good question. I appreciate that. I really appreciate that inquisitive mind. Any other questions? So if I go back to our share screen, dump, and share. So have we filled in all the numbers? 10 volt peak, 37 nanofarads, 966.67 ohms, 2.22 k ohms, 4.5 milliamps, 9 volt peak for the resistor, 4.35 volt peak for the capacitor, negative 25.80 degrees as being our angle of phase shift. What's after this guy? Oh, that was it. That was the last one. Okay, that's enough. So, my friends, as we close this session, and we went just a little bit over our 3 hours. We normally take 3 plus maybe a couple of minutes. So we're like at 4:41, 4:42. So we're going to be 12 minutes over our regular 3-hour session. Did you find this session helpful?
Yes, I did, big time.
Yes. But I do have a concern because I did this exercise last night and it's 3 hours. And of course I didn't finish it. I had another hour this morning and I still didn't finish it. So my concern is the amount of questions is 60 total. Would that be the same amount tomorrow? Because I'm afraid I'm probably not going to finish.
No, this is a good practice session, but this is not what your final is going to be in 2 different parts. As I've said, one part will be completely online. The other one will be online / on paper, and you'll just give me your numbers either typed into a word exercise or something of the sort. So no, your 3-hour period allotted for the final is more than enough time for what you're likely to see. So when Andrew asked the question, hey, Kogai, can we get some kind of hint what we might be looking at? So I threw in everything, including the kitchen sink. and that's why this one is so robust. But no, you will not have anywhere near this depth of stuff, this amount of stuff. You will be asked for different pieces of this. So that's why it's important that we went through all of this stuff. But yeah, so fear not. 3 hours is more than enough. Questions?
Will the filters be in there also or no?
Filters, yeah, filters were one of our most recent things that we discussed. And yes, filters will be a part of it. And so you want to look at your most recent notes with respect to filters, low pass, high pass, band stop, fundamentally what the shapes look like. And, you know, if you're shown a shape, can you answer what it is, what's happening? So yes, to answer your question, filters will be in there.
Okay.
Yeah, look at the notes that we've had for the past couple of weeks, because that most recent stuff will be in there. The only thing that I'm omitting is transformers. So transformers will not be a part of it. So if you see anything that looks like a transformer question, raise your hand, ask me. Because when we do the online portion, the questions will be mixed. And so one person's question may be different than another person's question. But still, if you see something that looks like a transformer question, raise your hands, let me know, and then I will make a note of it that you can skip that without penalty.
All right.
Okay. So, and that holds true for anything and everything. I can't give you hints. I can't give you nudges. I can't give you the answer. I can't solve anything for you. But if you have a question, I can clarify things for you, or maybe help rephrase a question so that you might understand it a little differently, or hopefully understand it a little better. So I'll be happy to do that. Just in case there's anything ambiguous, or maybe if I'm typing too fast, I'm dyslexic. So if I'm typing too fast and I invert some words, and you look at this, say, hey, Co, this doesn't look like proper English. What's up with this? And then you can raise your hand, and I will look at it and say, oh my gosh, my dyslexia crept in and I mistyped something. And yeah, I can see that it's ambiguous. So I will help clarify that for you and anybody else. So don't just sit there in a fog. If you're stuck on anything for more than 15 seconds, move on to the next one. Okay.
Got it.
Anything else I can share with you? Any other questions that you may have?
There's some stuff that I turned in late and stuff.
Yeah, I'll
are you
take care
gonna
of all the
grade
grades. Yeah, I will take care of all the grades. I saw your note. Thank you.
Okay.
I will get that taken care of for you, guaranteed.
All right. Thank you.
You're welcome.
That's
Any other
it.
questions?
I think we're good. Thank you for going over this for me and making this, and I appreciate it.
Well, no, I think the whole class appreciates your question. So
Yeah, thank
it's a
you,
very good
Andrew.
question.
This is a really good exercise for all of us.
Yeah. Prior to this, there was just a single sheet of topics, but no sample exercises to work through. So here's the topics. So we've gone through, and but I'm glad we were able to produce this document, and that it was helpful to everybody. So come tomorrow, everybody's understands the drill. Laptop with a webcam, I can see you. Have your cell phone ready so that I can see what the room looks like, and that your space is clear except for your notebook, and then you'll just have at it. That I need to be able to see all of your smiling faces on all the time on the Zoom, so that we can make sure that your microphones are on. So you want to make sure you're in an environment that is not going to be disturbing to anybody else. So if you happen to be in an environment where there's other people running around during the 3 hours that we're doing our final exam, you better be in a room where other people are not running around, where the window isn't open and the train isn't going by and the buses and the sirens aren't coming through, the sound of the buses and the sirens aren't coming through your windows. Is everybody clear on that? Yeah. So for 3 hours, for 3 hours, you're gonna have to find some way to have that space wherever you're at quiet, because your microphones have to be left in the on position. If it gets to be too noisy, then maybe we'll do something separate. But that is the other stipulation that you should be aware of. Okay.
Professor Coe.
That way I know. That way I know that there's no conversation happening on the side also. Everybody follow?
Yeah, Professor Coe.
What question?
Which class do you recommend to take after this session's over? Something that kind of follows up on this, so we don't jump around.
Oh my goodness. Yeah. Well, in the fall, what I will do is I will shoot out the fall schedule and then show you what is available. So in the fall, for anything after 50, the classes are in the evening. And so you'll have to look and see, which evening might fit your personal schedule. But I do have my favorites as to what I would recommend that it is that you consider taking.
Okay. And there'll be
Okay,
no classes in summer then?
Oh, no, you're going to see the schedule tomorrow. Yeah, I'll post the schedule, the fall schedule, what's proposed on our on week 17. Yeah, on our finals week. So you'll see it. And then we can talk about that for just a short bit before we begin the final exam while I'm going through looking at each of your setups.
Okay.
Yeah, so I definitely have some things to recommend for you, okay? A lot of good stuff. Let me tell you, really, really good stuff. So with that, my friends, I think you're off and running to the races. I will stick around with Mr. Lau because we need to work out some guidelines as to how we're going to administer his test. So with that, the rest of you have a most, let me stop the screen share and go back to here. Go back to here. Okay, picture for the dean. Do the matrix. Okay, here we go. Camera. And yay. Andrew. There you go, Kyle. All right, picture for the dean, 1, 2, 3, and smile. Yay. Good job. All right, my friends. With that, have a lovely evening. I'll stick around for Mr. Le. Take care.
Thank you.
Adios.
Bye.
Bye. So Mr. Lau, yeah, you wanted to leave your cell phone on too, because you need the two things on. So right now you have your computer screen on, which is good because you're going to need that. And then I also need to, so on your computer, you don't have a microphone. So what you need to do is you will log on two ways like you did just a moment ago. You will have your computer log in and you will also have your cell phone log in. Do you follow what I'm saying, sir? Mr. Lau, I can't hear you because you're...
I driving the computer.
Okay, so I see your name, Wenbin Lau. Are you on your cell phone now or are you on your computer? Which one is logged into Zoom?
Right now it's computer.
Computer. Okay, so your computer has a microphone, but it does not have a camera, yeah?
Yeah.
Okay. All right. So as long as it has a microphone, but it doesn't have a camera, at the beginning of our exercise, what it is that I need you to do is you need to log in with your cell phone also.
Okay.
And
Yeah,
just,
I think I need.
and so all you have to do.
Cell phone
yeah,
have the camera.
I know it's okay, but you use the cell phone for the camera for me. So you look at your computer, you can talk on your computer if you have a question, you can answer on your computer if you have a question. The whole idea regarding the cell phone is you're going to set the cell phone to one side where I can see you, okay? So what you do is you set this up. So you set it up. So in this particular case, I'm setting this up so that part of my face can be seen on the cell phone. Part of my face can be seen on the cell phone,
Oh,
and then yeah, that way I just need to see the student on the cell phone. So you just set this aside, down low on your table somewhere. Just put a book against it so I can see your head, your face, and then do your work on your computer. And leave your microphone on in a quiet room, okay?
okay.
Okay.
It's,
So, Mr. Lau, here's another thing also. Have you turned in a lot of work that was past due?
Robert's a path there.
Yeah, have you turned in old work is my question.
Where's the question?
Have you turned in your homework? Did you
No.
upload your homework into Canvas?
I'm not turning.
Because here's the concern, Mr. Lau, is right here, as I'm looking at your grade, Mr. Lau, you do not have a passing grade. Right now, your grade is at 49%.
I need
If you're at
60% or 15%?
49.
Oops. So what might go the how many percent will fine?
Well, you need 70% in order to pass this class. You only have 49.
So I need
So,
to gather this 21% to in canvas of the be fine of the canvas.
yeah, otherwise you're not going to pass the class. So here, I'm sharing the screen right now. Can you see can you see my screen on your computer, Mr. Lau?
Yeah, I see.
Okay, so these are your grades. These are the grades for Wen Bin Lao. And if I go all the way to the bottom right now, your grade is at 49%. That is not enough to pass. You need 70% to pass. Now, you still have 24 hours to be able to turn in a lot of missing stuff. So if you come up here to this part with the blue letters, you can see what's missing. So, for example, the things that are missing that I have assigned here, the practice final, I'll put that in, but you look for some big points. So what's some big point things that you've been missing? See right here, 0, 0, 0 on 110, 0 on 110. If you do these guys, you turn them in and they're correct, you can bring your score up, but you haven't done anything in week 10. There's a 0 here. You didn't turn that in back in week 10. And we're now at week 17. So that's 7 weeks ago. Here's another thing, series parallel analysis. That was a 100-point exercise. You didn't turn that in. Capacitance online exercises, review questions. These you did not turn in. So each week that you don't turn in stuff is going to hurt you. Don't worry about the lab manual. Everybody will have a score in the lab manual. But other things, big point things that you're missing will hurt you. See this one here, day 4 learning instructions, 150 points. Anything that's an online learning assignment, you should be able to do because those are just watching videos. So if you just turn in So let me give you an example. Let me help with this. So let's go here. Let's go here. And let's go, let's take a look. You were missing right here, 150 points. So week 4, a day, instructions for online learning assignments. So this is week 4. So here in Canvas, I'm going to go back to week 4. So here's week 4. And do you see in week 4 online learning assignments right here? You see this in Canvas, what I'm pointing at? Mr. Lau?
Yeah.
You see it's 150 points?
Yeah, I see.
So if I click this guy, watch what happens. It opens up. These are things for you to watch. And right at the beginning of each one of these is an Excel sheet. Right here, 0 is an Excel sheet. If you open up the Excel sheet, and you open the guy up, and you enable editing. Where's my Excel? Let me move it over to here. And then open this guy up. Okay, this is good. This shows that we have 15 videos for you to watch. Each one of these is a video for you to watch. So for example, this one here, DC current flow. How do you get to this video? You can just copy this guy, copy, and you open up a web page and you paste it and you enter it. And you play the video. DC current flow in a parallel path. Next, it tells you what's happening in a parallel. Next, next. So when you go through all of these, what you're going to do is you're going to enter a date. So for this one, oh yeah, I watched this one, so I will put in 5-19-20. That's when you finished it. And so whichever ones you finish, you put in those dates. When you have this all filled in with dates that you watched the video, that means you have watched all 15 of these. You save this, and then you upload it in Canvas. So in Canvas, you will upload it. So in Canvas, what it is that you will see for week 4 is this. I will go to Student View. Home. Leave. Home. Okay, I will go to Student View. And in Student View, in week 4, so close this guy, open up week 4. So here were the online assignments. You see all of this. So you want the Excel sheet, the XLS file that will give you this sheet. You fill in those dates, you save it, you put your name in it. See right here, it says by your first name, last name. So what you're going to do up here is you're going to type in when.
So I lost. What's the?
Okay, so you're going to type that in there. You're going to save this. After you save it, then you're going to submit it by hitting this blue button. I need to see this guy with all the dates filled in with your name on top, submitted here so you can earn your 150 points. So you can make up a lot of that percentage, that 21%. You could make up a lot of it by filling in some of your old homework that you have not done. How do you know what you have not done? Simply go to your grade sheet and you can see everything that you have a score on and some things you don't. So don't worry about the little stuff, the 20, 25, 30 point stuff. Don't worry about the little stuff. Go after the big stuff. 100 points, missing. You got nothing here. Okay. What else is big points? 150 points. That's the one we were looking at. You turn in this guy, all that's filled in after you watch the videos, you got 150 points here. That's huge. But if you don't turn it in, I can't mark a score for you. And if I can't mark a score for you, then you're staying down here at this percentage. And then we're going to see you again in this class another time, but you won't be able to pass. So can you see, you do something between now and the next day, you can turn in a lot of this missing stuff. Just look for the big numbers, okay? Look for what's missing. That's got big numbers. Can you do that? And that will
Okay,
raise your percentage, okay? Mr. Lau?
Big number 400.
Okay, leave student view. Okay, Mr. Lau, that's what I have for you. Do you understand what you can do between now and tomorrow? You can still raise your score.
I need to do that. Any
Yeah,
more?
you have to do a bunch of things, okay?
Okay.
Okay,
Oh,
okay. You can do it.
I can do it.
You can do it. Just get it done.
I cut it.
I will see you tomorrow, okay?
Okay. See you
Okay,
tomorrow.
have a good evening, sir.
Bye.
Okay, take care. Bye-bye now. Stop the share.